logic has been considered to be deviant logic, but there are some points of view, some thoughts which may provoke us to think again about the question, what is the status of paraconsistent logic? Any logic is a structure, as we all know that there is a language containing the theories and the formulas, and also the relation of deducibility, and there are some axioms, reflexivity, monotonicity, and transitivity. Classical negation is defined as in this way: for all x, t and not a, if x is deducible from t and not a, if and only if a is also deducible from t. That is the theory. So in contrast to this, if we go to paraconsistent logic, there are three definitions I want to mention. First, I'll mention EC, that is the theory that everything is derived from a contradiction. And the first definition given by Bejoux, and where paraconsistent logic is said to defined as that which rejects EC, and there is a special type of negation. The negation is defined in this way, that it is a negation if and only if there exists a theory T and formulas A and B such that it is not the case that B is derived from T, A and not A. The second definition is from Jaskowski and da Costa, who defined paraconsistency in terms of inconsistency and triviality. Inconsistency means, again, a theory T is inconsistent if and only if there is a such that A and not A both are derived from T, and trivial means if and only for every A is derived from T. So paraconsistent logic is that which is both inconsistent and non-trivial, and a logic with a paraconsistent theory, however, rejects EC provided it accepts the rule of transitivity. The third definition is a semantical definition, where the rejection of EC is defined semantically. There is a model and a formula A such that A and not A are both true in this model. And the traditional formulation of PC is like this: a sentence and its negation cannot both be true. So in this sense, paraconsistent logic is that which denies PC. Now, from these definitions, it follows that there are two features found in paraconsistent logic. One is that it denies the law of excluded middle. The other is that it disapproves the rule of disjunctive syllogism. So the question is whether paraconsistent logic is a deviant system or an extended system or any other thing. As I started earlier, that it is said to be deviant, but let us see what happens. Any type of non-standard logic we define in this way, that either it is deviant or it is extended. Extended means which considers classical logic as inadequate, and deviant means which considers classical two-valued logic as mistaken. So extended logic is defined in this way, that L1 is extended in relation to S2 such that the vocabulary, the common vocabulary they share, and L1 has some additional vocabulary, and the class of well-formed formulas of L1 definitely will include the class of well-formed formulas of L2. And the third point is that the class of theorems or valid inferences of L1 and L2, that is also different because there are extra theorems in L1, which includes the additional vocabulary. In case of deviant logic, we define in this way: L1 is deviant in relation to L2, such that the class of well-formed formulas of L1 coincide with the class of well-formed formula of L2, and the class of theorems differ. Quasi-deviant logic is defined in this way: L1 and L2 are quasi-deviation of each other if the class of well-formed formulas of L1 properly includes the class of well-formed formulas of L2. The class of theorems differs from the class of theorems of L2 in the sense that those class of theorems may have the common vocabulary or they may have the additional vocabulary. So in this way we define. Now it is a fact that the basic item which is of classical two-valued logic, which is challenged by the paraconsistent logic, is this: every inconsistent set of propositions explodes. This is of course. Mm. Yeah. Extend. Yeah, but the second part is that the class of theorems differ. In case of extended logic, that doesn't differ. It includes the class of the theorems of L2. Yeah. That is additional. But it doesn't, all of the theorems of classic L2 are included in L1, but here it's not so. It's not so. They differ also. The common vocabulary also, there is difference when the theorems have the common vocabulary. So the thing that is basic statements of classical two-valued logic challenged by paraconsistent logic is this: every inconsistent set of propositions explodes. So they deny, paraconsistent logic denies this. So what it gets, not every inconsistent set of propositions explodes. That means it speaks of that some inconsistent set of propositions does not explode. That is the theory. Now, it is quite compatible with the statement some inconsistent set of propositions explode, because they speak of some, they speak about dialetheism. They speak about some contradictions to be true. So in the context of some inconsistent set of propositions, they say that they do not explode, but regarding others, they have to admit that they do not explode. So there is some sort of compatible. So there may arise a philosophical question that can we, on the basis of this observation, think about paraconsistent logic as an extended logic? We can raise the question actually. Definitely the first we'll have the negative answer because it denies the law of extruded middle. So how can it be the extended system of classical two-valued logic? But there still remains the scope. Why? Because there is a further distinction between the law of excluded middle and the principle of bivalence. There is a distinction between the two, and on the basis of that distinction, we may raise the question: what is the kind of paraconsistent logic? Now, in Aristotle, as we find both LEM and PB, it is written in these two quotations that in the first case, it is necessary in every case either to affirm or to deny, and that it is impossible simultaneously to be and not to be. That is one quotation from Metaphysica. The other is that between two parts of a contradiction, it is necessary either to affirm or deny one thing of any one thing. So these quotations may lead to the conclusion that LEM and PB, they are the same. I would like to refer to Van Frassen, who distinguishes between the two in the sense that LEM is expressed in this way: any proposition of the form P or not P is logically true. And principle of bivalence is defined in this way: every proposition is either true or false, or equivalently, one of P and not P is true, the other is false. So principle of bivalence is a semantical law, and law of excluded middle is not like it. Now, Van Frassen advances two reasons to show that LEM is different from PB. And in the first reason, we have to refer to William and Martha Neal, and in the second reason he cites, there we have to refer to the concept of supervaluation. In the first case, before referring to William and Martha Neal, let us remember that in the book De Interpretatione, Aristotle refers to the question of the truth, the status of future contingent statement. In the first quotation, there is everything must either be or not be about to be or not to be. But in the second quotation, you see, it is not necessary that of every affirmation and denial of opposed statements, one should be true and the other false. For in the case of that which exists potentially but not actually, the rule which applies to that which exists actually does not hold good. That which exists potentially means future contingent statement. Now, Aristotle's these quotations have been interpreted by William and Martha Neal in this way. According to them, Aristotle's quotations will it is enough proof to show that LEM is the same as PB. And they say that it is a mistake if we distinguish between the two. They interpreted Aristotle's conception as in the following way: it is true that P equivalent to P. Now, in the first sentence, if we replace or substitute P or not P in case of P, then P or not P being the same as LEM, the other portion will be it is true that P or it is false that P. Is that clear? The first sentence is the interpretation given by William and Martha Neal about Aristotle. According to them, Aristotle says it is true that P equivalent to P. Now, in this sentence, if P is replaced by P or not P, then the other part will be, it will be true that P or it will be true, false that P. So, the left portion will be LEM and the right portion will be PB. So, according to William and Martha Neal, it is a mistake to distinguish between them because they are the same. Aristotle's quotation also says that they are the same. This is the view of William and Martha Neal. Now, Van Frassen says that this derivation works under two wrong presuppositions. Presupposition number one is this, that when we said P is equivalent to it is true that P, he says that only P is a sentence in object language. P stands for any sentence, that it's not raining, the sun is shining, it's hot, etc. But it is true that it is raining, it is not a sentence in object language. It is the sentence in meta language. So P is never identical with it is true that P. That is the first presupposition, without understanding which William and Martha Neal gave that equation. That means P is equivalent to it is true that P. They didn't distinguish between the object language and the meta language. Because in the previous one, it is P. No. That the first sentence, that is their interpretation of Aristotle. It's not actually the interpretation that Van Frassen wants to say. This is the first reason, first presupposition, that they didn't distinguish between the object language and the meta language. And the second presupposition is this, that William and Martha Neal defines it at P if and only if it is true that P. That was earlier we have seen. Now this principle justifies any argument of the following form: dash P dash, hence dash it is true that P dash. And the opposite, that is negation, it is true that P dash, hence dash P dash. So in both the ways they can be derived, which Van Frassen questions. He says that these two derivations are wrong because here P is a part of a bigger sentence, and when P is a part of a bigger sentence, it can never be replaced or substituted by it is true that P. So what will be the correct one? Correct one will be P, hence it is true that P, or it is true that P, hence P. So it should be the proper form. So without using the term equivalent, he uses the term deducibility. Hence means therefore. So these two arguments are valid. It proves that they are truth preserving. Truth preserving means that it is never the case that the premise is true and the conclusion is false. But we have to remember that it says nothing about the truth value of the conclusion when the premise is false, or the truth value of the premise when the conclusion is true. So it has got nothing to do with the truth and falsity of the situation. It only says that it is a valid argument because it is never the case that the premise is true and the conclusion is false. P means it is a sentence. It stands for any sentence. No, not mixing. Here it is written hence. Hence means hence means it is the therefore. Mm. It follows. It follows one. It is deducible from the other. But if I write P is equivalent to, it is true that P. Yeah. No, according to Van Frassen, P here occurs only as a single statement. It stands for any sentence. It is raining or it is hot, etc., etc. So from there, I can deduce that it is true that P. It is true that it is hot. From that, we can write it, or from the event that it is true that P means it is hot. It is true that it is hot. I can write it is hot. It follows. So it is simply one is deduced from the other. Actually, it follows from the quotation that Aristotle uses. So from the quotation it follows. Van Frassen derives it from the quotation of Aristotle. He is not creating it by. So here the point is here that when William and Martha Neal, they considers dash P dash, therefore dash it is true that P dash. So there, according to Van Frassen, P occurred as a part of a whole sentence. So if it is a part of a whole sentence, then that portion of P cannot be replaced by it is true that P. Only when P occurs alone, then from P we can deduce the conclusion it is true that P. That is what Van Frassen says. Now, he also says further that as because here in their interpretation, William and Martha Neal's interpretation, LEM and PB are identified. So if we identify them, then again there will be two fallacious arguments that will follow from the identification. Argument 1, number 1, if P, as you remember that the sentence is P if and only if P. So from P if and only if P, we can write if P then it is true that P, because it is a biconditional. So from biconditional I can write one portion of it. P equivalent to it is true that P. So I can write if P then it is true that P. One side of the biconditional. Then I replace P by not P. Then if not P, then it is true that not P. Right? Then I can use LEM. LEM means, as I have earlier said, LEM means P or not P. So using LEM, this third sentence, and using the first two sentences by using constructive dilemma, we can get the conclusion, it is true that P or it is true that not P. The conclusion follows. But according to Van Frassen, it is wrong. Why? Because from this third sentence, P or not P, the fourth statement doesn't follow. The fourth, in order to deduce the fourth statement, it is true that P or it is true that not P, we need this 3-star statement, either P is true or not P is true. Until and unless this is used, either P is true or not P is true, we cannot deduce the conclusion, it is true that P or it is true that not P. Why? Because in the first two statements, there is nowhere mentioned whether P is true or not P is true, whether P is false or not P is false. The first two statements only say that the argument is valid, means the premise is true and the conclusion false, it cannot occur. That is the only thing. So in this case, the third statement, either P is true or not P is true, it is to be used if we are to derive the fourth statement, the conclusion. But the third statement is not the law of excluded middle, as in the previous one. In the previous sentence, it was the third statement was LEM. What was LEM? P or not P. And in the next slide, we see that it will be either P is true or not P is true. If we can add this third statement as an additional premise, then only we can get the conclusion from the first two premises taken together. So, Hmm.
So that classical thing is then being denied also.
Which one?
If we say A or B, A implies something, B implies something.
A or B. That is why it is supposed to be valid. It is supposed to be valid. But he is denied because he says that the conclusion, that as the conclusion says, it speaks about the truth of P and not P. And the truth of P and not P is not mentioned in the first two statements. That is the mere formal validity. When the first, look at the first, this is not the argument actually. In the previous one, P, hence it is true that P. In this whole sentence, from P we derive it is true that P. But I don't know about the truth and falsity of P. I only say that it is a valid argument because it can never happen that the premise is true and the conclusion is false. Truth and falsity is not spoken about in those statements. But here, if we are to derive this conclusion, we need this third statement, either P is true or not P is true. Until and unless this third statement is there, the fourth conclusion cannot follow, so far as truth and falsity is concerned. Is that not clear?
In some sense, then, that implication itself is being denied. Then we should
Now you see, if P, actually the point is that the first sentence, if P, then it is true that P, it is a part of the original sentence, P is equivalent to it is true that P. That interpretation is denied by Van Frassen. And as he has taken, they have taken the first sentence from the wrong interpreted sentence, that is why it is following. The first sentence, that, yeah, of course, yes, because the third sentence, because in order to fit the argument, they are using the LEM in that form, and they're trying to conclude this. So this is a case where now there is an argument B. Another argument also follows. The same thing, the first premise is again false because it is taken from the wrong interpretation. If P, then it is true that P. Then by changing it, if not P, then it is true that not P. Now if we contrapose it, then we will find, if the first sentence, we will find if not it is true that P, then not P, then not P. So by using 3 and 2, again, by transitivity, we get the fourth sentence. By using transitivity. So if not, it is true that P, then not P. If not P, then it is true that not P. So using 3 and 2, by applying the rule of transitivity, we get the conclusion, if not it is true that P, then it is true that not P. So as the whole thing is denied by Van Frassen, because he says that if we are to derive anything, from these two premises and the additional one, we have to do this one. That means the first two sentences are like before, as we saw before. P, hence it is true that P. Not P, hence it is true that P. Now, the third sentence will be P is false, hence not P. Then, fourth sentence will come, P is false, hence it is true that not P. So here also the third and the second, we are thinking about the transitivity, that P is false, hence not P. Not P, hence it is true that not P. So P is false, hence it is true that not P. So it follows only if we take as the first and the second premise, these 1 star and 2 star, these two statements, and the third one as this starred sentence. Is there anything, is there any problem? Please ask me. I'll explain. Please tell me. Now, which one? The interpretation? No, actually there is an interpretation.
When you say P, hence it is true that P.
Huh.
That means
Yes, that means a contradiction. I can, if I assert the contradiction.
Not
that
assert, you just write the contradiction.
The writing is the assertion.
This is the writing, okay.
If I write P, that means I am asserting P,
Oh,
whatever
okay.
be the P, true, false, contradiction, whatever it is, then from that it follows that it is true that P. P means true or false or contradictory. That is the derivation.
No,
it is deducible. It is deducible. That is the interpretation.
No. When we say deducible, it means either it is deducible in some syntax or it is deducible in some semantics.
Yes.
Where is it? Is it deducible in a syntax?
Syntactically.
Then what is the syntax? Is it is true?
Yes.
Is it a component of the syntax? It is true that, is it true? Is it true that?
No, it's not the component. But as if you go back to Aristotle's quotation,
I understand. So I will not accept Aristotle's quotation itself.
that is
Yeah, yes, of course.
that you may.
Of course.
That
Because
you may
there
do.
is the, Aristotle didn't make much difference between the syntax and not syntax, meta language and object language, etc., which you are mentioning here. Actually, it is true that should come in the meta language. You
Of
mentioned
course,
itself.
true, yes.
So
but
you cannot derive a meta-linguistic sentence from an object language sentence.
actually, I think in order to show that the equivalence is wrong, P is equivalent with it is true that P. That is why Van Frasson thinks about the deducibility of one from the other. No, but as William and Martha Neal identified LEM and PB, then in order to distinguish between because one is a semantical rule, other is not. So we have to show that they are different. In order to show that they are different, until and unless I go through the interpretation given by William and Martha Neal, I cannot show that they are different. In order to show that they are different, I have to go by the interpretation. So in order to find out there is the fault in the interpretation, I have no other way but to enter into this discussion.
But you just said that one is syntactical and another is semantical. So is that enough?
No, it is merely the interpretation of Aristotle which is of utmost importance here. He says, according to Van Frasson, P equivalent to it is true that P, it is not the proper interpretation of Aristotle. And if we write P it is equivalent to P, it is true that P, then you have to identify between LEM and PB. And as because there is a distinction, syntactical semantic distinction, that is why I think yes, I support it because I have to distinguish between those two things. The interpretation I cannot accept. P is equivalent to it's true that P. In order to deny that distinction, the interpretation, there is no other way than to go by this the argumentation. What to do? So yes, now the sentence B, it is actually the sentence which is the interpretation of Van Frasson when he speaks about Aristotle's quotation. Then you will find that it is completely semantical statement. It is true that P, if and only if, it is true that P. It is the interpretation of Van Frasson of Aristotle's quotation. So, it is meta. It is true that that is meta. It is true that P. Yes, of course. But the quotation is such that one can be true, the other cannot but be false. So we have to interpret it in that manner. I have gone through many literatures in this regard in Van Frasson, and I found that everybody supported this interpretation. Now reason 2. Reason 2 is that we have to refer to the theory of supervaluation. It is also referred to by Van Frassen that there are exactly two valuations in classical two-value logic, V1 and V2, and supervaluation is identified as S. So suppose there is a property F, and A is a referring name, B is a non-referring name. Now, in this table, we can very easily find that B is a non-referring name, so FB is neither true nor false, because it is a non-referring name. It is neither true nor false. And as neither true and nor false is not having place here, no value can be shown to be neither true nor false. So PB is not active here, PB. But in the case of FB or not FB, LEM is active. FB or not FB is true, because FB or not FB, the table shows that in either of the case it is true. Either FB is true or not FB is true. In that case, FB or not FB will be true. So LEM is true here, but PB is not. PB means where we say that there is some valuation which is neither true nor false. Is that clear? No. No. That also I tried to, if we write FA, A here, substitute A here. Yes. I don't know. That means that if it is now that is it is to be interpreted as A by A. It is to be substituted by A. In that sense, it is true. No, not in the sense of B. Not. Yes, that is, it should not be there. Right. It should not be there. Because, yes, that is the, there should be a gap. There should be a gap. Truth-value gap. So, but the point is that FB or not of FB is true, but as something is there which is neither true nor false, there is no such value. So, PB is not holding here. Now, it has been mentioned that LEM need not be rejected by many-valued system. That is the claim. Now, people may say that in Lukasiewicz's system, definitely it denies law of excluded middle, right? But what it is said here, simply that it is not unconditionally possible. When Rescher refers to this point, that in Lukasiewicz's system, the disjunction V, if it is replaced by another relation, that means P or Q for not P, arrow Q, in that case, you see, P or Q, the table should be, if P and Q both are indefinite, then the value, if the value is 1, in that case, we can try to retain LEM. It's not saying that in Lukasiewicz, LEM is retained. It is simply says that Rescher tried to show that three-valued logic is possible without rejecting LEM. That is the point. It's not that Lukasiewicz is doing it. It is Rescher's interpretation. Now, there are other thinkers also in case of Smiley, in case of Kleene. There are 4 values. It is sometimes said that those 4 values are actually epistemological variants. By saying this, we try to retain PB. In case of this logic, having the 4 values, we may try to retain it. Sorry. in these cases, I want to say that they are not saying that there is, actually there is the rule of PB. PB is applicable here. It is simply said that PB can be retained if we consider that these four values are not the four values, they are the epistemological variants of the two values. So it is said that the point is that many-valued logic is unconditionally possible without rejecting LEM. Lukasiewicz's system rejects LEM, but we can construct a three-valued logic where LEM is present, LEM is retained. That is the point. But PB, if in order to accommodate PB, principle of bivalence, we have to adopt some ways of thinking. For example, in case of those four values, we have to think that they are the epistemological variants of true and falsity. So until and unless we interpret those four values in that manner, we cannot say that PB is accommodated. So PB cannot be accommodated. Until and unless, so unconditionally not possible. But it is, many-valued logic is unconditionally possible in this way. Now, it is very clear that paraconsistent logic is unconditionally possible when it rejects LEM. So it cannot be considered to be a variety of many-valued logic in that sense. Rather, it entertains both the propositions. Some inconsistent set of propositions does not explode, and some inconsistent set of propositions explodes. So can we think of it as extended? Again, the answer is negative, because we know that it is very much different from two-valued logic, as it rejects the law of extruded middle. So what should be the stand? What stand should we take? So here we may think about asking a question to paraconsistent logic. What kind of contradiction is that? They are thinking about contradictions to be true. P and not P true at the same time. So the question is, are P and not P true under the same circumstance? That is the question. If that is the question, the answer again can we get from belief sentences. So it is possible that they can be true and not true from the same standpoint. And so the only stand we can take is that paraconsistent logic approves contradiction only under specific cases, but not generally. If we take this stand, so then we can consider it not as deviant, not as extended, but as non-deviant. It is a weaker claim, I should say, because many people will stick to the point that definitely they are deviant system. So if it is found to be neither deviant in that sense, why not deviant? Because it is not the same as many-valued logic. Deviant definition we have already given. It is not many-valued logic, because in many-valued logic we can continue with many-valued logic while we maintain LEM. Only that PB is to be denied. So there is a fine distinction between the two. And if there is a distinction, then we cannot identify paraconsistent logic with many-valued logic. So that is not deviant. And that definitely that is not extended, because it denies the law of extruded middle. So what kind of logic is it? We can say it is non-deviant. Non-deviant, the term actually non-deviant actually has not been made clear till now. Trying to find out some other definition of deviance. What can be the other kind of deviance? Means what? Only those 2 points, or there may be other points we can add to the definition of deviance. So let me see that. That's all I wanted to say. Now I request Angana Chatterjee to come and present her.
Just a quick check. People online, can you hear and see the slides?
Yes, we do.
Oh, okay.
I can see the screen.
Yeah, okay. So, Walter, you can hear us. Hi, Walter.
Hello, morning, good day.
Yeah.
It's very early in the morning here.
Okay, so you can hear us. So, you can also see the screen, right?
The screen, yes, I can see the screen.
Okay.
Now I see the slides. Was there any change in the schedule?
Walter, did you ask something?
Yeah, I mean, was there any change in the schedule? Because I was thinking I would be talking now, but apparently there's no problem. That's okay for me. Just to know if there was any change in the schedule, any modification.
We are running just a little late, but.
Okay. Okay, no, that's fine. That's fine.
But your talk is tomorrow as per the schedule.
Tomorrow is not 18th? Yes, tomorrow, right. Yeah, it's on 18th, not at 17th. Yeah, right.
That's okay with you, right?
No, that's fine.
Okay, great.
No problem. That's okay. I'm following you guys.
Good evening, everyone. The topic of my today's talk is Contradiction, Copernican Revolution, and Corollaries on Negation. I would like to reflect or propose 3 hypotheses on negation. Number 1, Copernican Revolution in logic. 2, conservation of information in logic. 3, observer effect in logic. So, in order to address the concept of negation, we need to first address the existence of contradiction. In nature, in science, in data, there are several examples found which claims that contradiction exists. Here I mentioned only one experimentation that was done in 1801 by Thomas Young, that is double slit experiment. A short picture is there. I'm not going into detail, but I'm just giving the outline of this experimentation, that it says, double slit experiment claims that wave and particle, light and wave behave in the same manner, though they seem to be contradictory, because light do not have mass, whereas wave have. Now, what is the relevance of the existence of contradiction in reality or in empirical science here? To understand this, we need to focus on the concept of anti-exceptionalism. The term was coined by Williamson in 2007. Anti-exceptionalism in logic is the view that logical theories are not fundamentally different from scientific theories in how they are developed, justified, and revised. What is the empirical basis of that? It argues that logic, like scientific theories, can be evaluated and revised based on empirical evidence and pragmatic considerations, rather than being seen as infallible or purely a priori. That is the most important part of this. Anti-exceptionalism says that it's not a priori. So it claims that there has to have the evidence from empirical world. Now, in classical logic, we all know the notion of explosion, that contradiction leads to explosion, hence triviality. How this deduction happened, I showed here. So P is a statement, curl P, second premise. We can add whatever we want. Here I added Q. And then by disjunctive syllogism, it was followed that Q. So anything and everything follows from contradiction. This notion is called the theory of explosion, which leads a logical framework into triviality. Paraconsistent logic allows for some contradictions to not to lead to explosion. And one way that logician used to accomplish this is to reinterpret the steps of the above deduction. So there are addition, there is disjunctive syllogism. Okay, so one way that logicians use to accomplish different interpretation. Now, in order to understand this different interpretation of this deduction, we can just have a quick look into the concept of dialechism, which was introduced by Graham Priest. We already mentioned the term contradiction. Now, there are many types of paraconsistent logic. Dialechism is one of them. To be more specific, dialechism can be the philosophical motivation of framework of paraconsistent logic. And what does it claim? It claims that some contradictions are true. We already mentioned earlier that paraconsistent logic allows for some contradictions, not all, for some contradictions not to lead to explosion. So, dialechism claims that some contradictions are true. Now, when it's a matter of contradiction, it's a matter of negation. Why? Because contradiction, the syntactic structure of contradiction is like that. We know that contradiction consists of conjunction of a proposition and its negation. One way to prevent explosion from contradiction could be to re-examine the semantic content of negation operator. In this context, I want to propose this term, Copernican revolution. Why I want to do, I will explain later. In the sense of dialethia, we know that dialechism claims some contradictions to be true. Now, let P and not P be a true contradiction in the sense of dialechism. If P is true, then in classical sense, curl P would be false. Now, we propose a modification of the negation operator. Now, in this context, the modification would be like, suppose not P is not false, but some other truth value X. This prevents the derivation of any proposition from a contradiction that we mentioned earlier. Because if it's so, then here, number 3, curl P vel Q. So if curl P is not false, that we cannot deduce with the help of disjunctive syllogism this way. So the derivation has to have a different interpretation. Now, this may mean that the negation operator itself is not operating in the traditional manner or in the classical manner in dialechism. One may ask, what is the cause or what brings about this transformation of negation operator? One agent of this transformation could be the concatenation of the negation operator with a specific proposition P in dialethia, where we are specifically claiming some contradictions to be true. Using this line of argument, we are led to a phenomenon that can construed as a Copernican revolution for the unary operator of negation. Why Copernican revolution? Because we know about the Copernican revolution, where there is in the world of astronomy the shift of geocentric to heliocentric theory. It is quite analogous to here also. If we see a bit closer, this is as follows. The act of concatenation of negation operator with a proposition P classically transforms the truth value of P As we know, the statement, if P is true, then curl P has to be false. But we hypothesize that this concatenation also transforms the semantic content of the negation operator itself, which is expressed by the fact that curl P is not false when P is true, but has some other truth value X. So we cannot determine the state of a contradictory position, whether this is true or not. Because in classical sense, we can easily say that if P is true, then curl P is false. But in paraconsistent logic, in the sense of Aletheia, we cannot propose this. We cannot claim this. So we can say that the meaning of the negation operator depends on the concatenation of this negation operator with a proposition. So it cannot function in isolation that way. From this notion of Copernican revolution, another notion may be followed, that is conservation of information in logic. If P is true and P impacts the negation operator such that curl P is not false, but has some other truth value X, which we were discussing earlier, then curl P is not true either. Therefore, curl P is not equivalent to P. Therefore, the rule of double negation, which is a fundamental law of classical logic, does not completely eliminate the impact of the first occurrence of negation operator. So, we may hypothesize that this phenomena as conservation of information in logic, because in this case, the information which is getting conserved or preserved, that is, the proposition P was negated once. If I say that P is equivalent to double negation P, then we may lose the information that P once negated. So this information is preserved here. Now, from the notion of conservation of logic, conservation of information in logic, we can deduce this, another notion, that is observer effect in logic, which was implicit in the concept of Copernican revolution. We noticed earlier that the concatenation of a proposition with the negation operator may transform the meaning of negation operator. This may be construed as follows. Any particular proposition P is a certain observer of the negation operator, and the meaning of the operator is determined only when the observation via concatenation with P is done. The meaning of this operator is indeterminate in isolation, which I mentioned earlier. That the meaning of negation P cannot be determined in isolation. It has to be in concatenation with a proposition, in the case of Aletheia. And why I proposed it to be observer effect? Because an analogous situation is available in physics, which is known as the observer effect. In particular, physicists found that the observation of quantum phenomena by a detector or an instrument can change the measured result of the experiment. Now, it's my final, I may say that this is my final direction. I haven't gone through yet, but I would like to reflect on this and would like to have some feedback from you. That paraconsistent logic takes a modified meaning of truth that allows coexistence of contradictory statements. We know. There is a concept of tautology in paraconsistent logic, especially the system done by Graham Priest, that is logic of paradox. There are three value, true, false, and paradoxical, true and false. So we know that in classical sense, when we determine the status of a proposition, whether that is tautologous or not, we use truth value, and we see the whether the true, whether the each and every row of final column is fulfilled by the truth value true, then we say that this is tautologous. in this case, if the outcome is D, right, like designated value, which is true and P here, then the proposition is said to be dodology, that is LP tautology like, it's something written there. And we know that necessary truth is tautology. Now, in future, we'll try to understand, I don't know whether this question is quite relevant or valid or not, but somehow I went through it, whether the notion of dodology come close to the notion of necessary truth, because we know tautology is necessary truth, and if it's a matter of designated value, then whether these two notions can come close or can be. So this is my future investigation, and I'd like to have some feedback from you all. Thank you.
I now request Javed Hassan to present in brief his findings.
Good afternoon, everybody. From B.K. Motilal to Jonathan Ganeri, and from Graham Priest to Fabian Shang, all of them are tried to see the Indian philosophical logic in terms of modern Western logical framework. Following their motivations, today I get motivated from them and trying to see whether Buddhist logic has really some character which are considered to be as paraconsistent, or we are forcing it to fit with this thought. This is the topic. What I'm going to present here is a part of my PhD thesis under supervision of Professor Shannal, Professor Monideepa Shannal. These are the outline of my paper here. Nagarjuna Foundations of Knowledge, the middle way, and there are some technical epistemological notion introduced by Nagarjuna in Mulamadhyama Karika, Shabhava and Chatushkati. So let me introduce my topic. Nagarjuna is undoubtedly one of the most influential figures in the history of Buddhist philosophy after Dinnaga and Dharmakirti. He presented a philosophical system that radically diverged from classical logic. His philosophy of the middle way centered on the concept of emptiness, shunyata, has profoundly impacted Buddhist thought across Asia, particularly in India. Although Nagarjuna's emptiness is complex and often misunderstood as a concept. This paper delves into the argument that Nagarjuna's system represents a radical departure from the classical logic, particularly in its rejection of the principle of explosion. Thus, this study will attempt a novel interpretation of his logic, highlighting its implications for contemporary epistemology and logic. There are some key concepts. one of the most important concept is Tetralemma, Chatushkati. Here I am going to talk about. This is the foundation of knowledge of Nagarjuna, that the middle way represents Nagarjuna's attempt to avoid the extremes of eternalism and nihilism. Eternalism posits the existence of things as unchanging and permanent entities, while nihilism claims that things do not exist at all. Nagarjuna's concept of emptiness offers a third path, a middle ground that transcends these two extremes. Nagarjuna's philosophy has been immensely influential. His ideas were carried forward by and developed by subsequent Buddhist thinkers, leading to various interpretations and school of Madhyamika. Nagarjuna focus shifts the epistemological inquiry from the direct examination of the nature of perception, inference, and other epistemic notions to the more fundamental question: how do we establish the validity of these notions themselves? He identifies the three potential approaches: mutual coherence, self-justification, and mutual justification between notion and objects. While dismissing the first option as insufficient, Nagarjuna primarily challenges the notion of self-justification and mutual establishment. Central to his critique is the concept of Shabhava, or inherent existence. Nagarjuna argues that neither epistemic notion nor objects possess an independent, self-sufficient nature. This undermines the philosophy of their self-justification or mutual validation. By questioning the foundational assumption about the nature of knowledge and its sources, Nagarjuna invites a radical rethinking of epistemology. His analysis lies the groundwork for his broader critique of reality and the nature of existence. Nagarjuna's critique of Shabhava has profound implications for logic and epistemology. By denying inherent existence, he challenges the notion of self-justification and opens up a space for a more nuanced and relational understanding of truth and knowledge. His work invites a re-evaluation of the foundations of logical reasoning and encourages a critical examination of the assumption underlying our claim to knowledge. This is the central point, that is the problem of origination in Buddhist epistemology. Yes, ma'am. So I quote from Nagarjuna that if things arise from themselves, that is absurd. If things arise from others, that too is absurd. If things arise from both, that is absurd. If things arise without a cause, that is absurd. This verse encapsulates Nagarjuna's dialectical method. He presents four possibilities for the origination of things and then demonstrate the absurdity of each, effectively undermining the concept of origination as a self-sufficient entity. And here, this is the argument. The Nagarjuna poses four possibilities, then proceeds to show the contradictions inherent in each of these options. If something arises from itself, it must have existed prior to its origination, leading to an infinite regress. If it arises from others, then it implies creation from nothing. The other two options are similarly shown to be untenable. By demonstrating the absurdity of all possible explanations, Nagarjuna undermines the concept of origination as a stable and independent entity. Nagarjuna's epistemic logic offers a rich and insightful approach to knowledge and reasoning. It emphasizes on multiple perspectives, critical inquiry and non-duality, empowered individuals to develop knowledge, navigate complexities, and make informed choice on their journeys of understanding and experience. the world. The concept of emptiness is foundational to Nagarjuna's epistemic logic. Emptiness, which does not imply nihilism or non-existence of phenomena. Rather, it challenges the notion of inherent existence or self-nature, that is Swabhava. Things exist in dependence on other factors, but they lack an independent, unchanging core. This interdependent nature is what Nagarjuna terms emptiness. And the other important epistemological term is Pratitya Samutpada, which means dependent origination, is another conceptual term. It means that things arise in dependence on other factors without inherent existence. As you know very well that classical logic, the foundation of classical logic, is characterized by several fundamental principles, including the law of non-contradiction, the law of excluded middle, the principle of identity, and the principle of explosion. Now, Nagarjuna's logic offered a radical critique of conventional logic and ontology. It has profound implication for our understanding of reality. It suggests that our conceptual framework and logical categories are inadequate for grasping the ultimate truth. As he said, that reality is not a fixed, static entity, but a dynamic interplay of interdependent factors. He extensively employs the Tetralemma, Chatushkoti, a logical construct that offers 4 possibilities for any proposition: affirmation, negation, both, and neither. Now, he has introduced a many-layered notion of truth. Nagarjuna's concept of emptiness rejects rigid and fixed notion of truth, as we said earlier, influenced by the core Buddhist concept of emptiness and non-duality. Buddhist logic challenges rigid categorization and embraces the possibility of multiple truth coexisting. This opens door to a new ways of understanding paradoxes and navigating seemingly contradictory situations. It understands reality as dynamic and interconnected, where absolute truths and polarities like true and false dissolve into a wave of relationship and perspectives. Buddhist distinguishes between relative truth and based on our limited perceptions and interpretations, and absolute truth, which points to the ultimate nature of reality beyond concepts and dualities. Relative truths are valid within their context, but ultimately point toward a deeper reality of independence and emptiness. Interdependence and emptiness. Okay. Apart from that, the 4 noble truths at the core Buddhist teaching offers a framework for understanding suffering and its eradication, highlighting the relative truths of our current condition and path toward ultimate liberation. Instead of seeking abstract and intellectual truth, Buddhism emphasizes experiential understanding and personal transformation. Thus, truth in this context becomes a liberation from delusion and a journey to a deeper understanding, compassion, and interconnectedness. Therefore, Buddhist philosophy distinguishes between conventional truth, Sambriti Satta, and ultimate truth, Paramartha Satta, which resonate with paraconsistency, ability to handle inconsistencies within specific frameworks without invalidating the entire system. This is the Buddhist Chatushkoti, the structure of the Buddhist Chatushkoti. Both A and not at the 4 corners, there are A, not A, and both, and neither. In Western classical logic, the the law of non-contradiction state that something cannot be both A and not A at the same time and in the same respect. It is a fundamental principle underlying rational classical thought. On the other hand, the Tetralemma allows for possibility of both affirmation and negation, seemingly violation this law. The Tetralemma, a logical framework used by Nagarjuna and other Madhyamika philosophers, offers four possibilities for the proposition: is not, is both, is neither. At first glance, the third option, is both, seems to directly contradict with law of non-contradiction. However, Nagarjuna's perspective is far more nuanced. Nagarjuna did not intend to affirm logical contradictions in the ordinary sense. Instead, he was pointing out the limitations of language and conceptual thought in grasping the nature of reality. The Tetralemma is a tool to dismantle dualistic thinking by showing the inadequacy of both affirmation and negation. It points towards a middle ground that transcends conceptual opposites. Therefore, while the Tetralemma might appear to violate the law of non-contradiction, it's essential to understand that Nagarjuna's logic operates on a different level. He may not propose simply logical inconsistencies, but rather demonstrating the limitations of binary logic itself in grasping the ultimate nature of reality. Therefore, the Tetralemma here is a method to deconstruct conceptual frameworks and point towards a deeper understanding beyond language and thought. In essence, Nagarjuna's Tetralemma is not a challenge to the whole system of logic, but a challenge to the limitations of binary logic. So now I have shown that how the Chatushkoti violates this law of excluded middle and the other fundamental principles of classical logic. And then I've shown that how Nagarjuna depart from the classical logic. Since I don't have much time, so I'm skipping these slides. Now I'll conclude with two observations. That is the point of intersections among Nagarjuna's logic, many-valued logic, and paraconsistency. The Tetralemma, a core principle in Buddhist logic, proposes four possibilities for any propositions: true, false, both, and neither, true nor false. This challenges the binary nature of classical logic, which adheres the law of excluded middle. The Tetralemma can be seen as precursor to many-valued logic, which introduced truth values beyond true and false. Many-valued logic, a branch of formal logic, introduces more than two truth values. It offers a framework for dealing with ambiguity, vagueness, and uncertainties, which are central concerns in various fields, including artificial intelligence and computer science. Nagarjuna's logic, with its emphasis on interdependence and the denial of inherent existence, can be seen as a form of a proto-paraconsistency. By acknowledging the possibility of contradictory truths, Nagarjuna avoids the explosive nature of classical logic. And the second observation is this, that Nagarjuna's logic, while ancient, offers valuable insight into contemporary logical challenges. His epistemic logic provides a framework for analyzing complex and contradictory situations without succumbing to the logical chaos of the explosion principle. Though analyzing and examining the intersections among Buddhist logic, many-valued logic, and paraconsistency, we can gain a deeper understanding of the nature of logic, truth, and reality. That is, it offers a more flexible and adaptable approach to reasoning, which may consider to be essential for understanding the intricacies of human experiences and the nature of reality. And these are the future directions. I have to work in my research. The Tetralemma can inspire the development of more sophisticated many-valued logic that capture the complexities of human reasoning, and the emphasis on interdependence in Buddhist logic suggests a dynamic approach to truth, where propositions can change their truth value based on context. This could lead to the development of temporal and contextual paraconsistent logic. Moreover, by formalizing concepts like dependent origination and the Tetralemma, new paraconsistent logic can be developed with some unique properties. And some other, these are the references. Basically, I followed Graham Priest and Fabian Shang and some other journals. Thank you.
Okay. In the interest of time, no questions from the offline participants. It can be taken later during tea after the session's over. Let's see online if there are any quick questions. From the online participants, is there any quick question that you would want to ask either Professor Monidipa Shannal, Ongona or Javed? Okay, so in that case, let's move on to the next talk. The next talk is by Shorav.
Well, as a as a convener also, I cannot say that thank you to the conveners for inviting me. But anyway, so let's start. Since I understand that we are running 30 minutes late, so I'll try to finish as soon as possible. But I don't know whether it's possible to finish in 30 minutes, but okay, I'll try as soon as possible. Well, so এটা তো হ্যাঁ তাহলে তো okay, now it's working. Okay. Well, so the outline is that I'll quickly first talk about the construction of Boolean valued models of the classical set theory. Then we'll then go to the then we'll talk about the generalized algebra valued models. We'll generalize the idea of the Boolean algebras to the general algebras, and then following the same method, we'll come up to the models of some other set theories. And then from there, we'll talk about the non-classical algebra valued models of some fragment of ZF and full ZF. And we are not saying or, but and full ZF. Few things we'll talk about here. And then inside those models, which kind of mathematical foundations we are getting, that we'll discuss a bit. And then, though it is written here, the independence set theoretic results in some non-classical set theories, but as we have discussed that after me, Giorgio's talk is there, so Giorgio will take care of this point. So though it is there in the slides, I'm not going to explain it. So Giorgio will go to that. And at the end, I'll talk about a new interpretation function. Okay, so why that is needed and what it will actually do. So we'll discuss one by one. Okay, so let's go to the first point, that the definition or the explanation of the Boolean valued models of the classical set theory. How this model is constructed? It's simple that we first start with any model V of the classical set theory. Any model we start with V. Inside this V, we take a Boolean algebra B, and then a complete Boolean algebra, I should say. And then what do we do? For any ordinal number alpha, we make a class V alpha B, which is of this form that it contains functions. Simply, the functions are what? The domain of the functions are some functions created in the previous level. So like step by step we are creating, and then at any step you come, for example, suppose if your alpha is 10, you are actually you want to see what V10b is. V10b contains some functions where you take a function from here, its domain contains some functions which are created in the previous levels, like V0, V1, V2 till V9. So you take few functions from there, put them in the domain of this X, and the range of this function is simply a subset of this Boolean algebra taken. That means at every stage we are making some functions where the domains contain some functions previously created and their images are some elements of the Boolean algebra. That's all. And then what? Finally, you take the union over all these ordinal numbers. You take all these, all these collection, and then take the union. All these functions together form this collection VB. So what VB is very simple. It contains some functions whose domains are again some functions, and images are the Boolean algebras, like the value of the Boolean algebra we started with. Okay. Then what? Then actually we are aiming to show that this becomes a model of classical set theory. How it will be a model of classical set theory? Before that we have to define the interpretations. So we are going to that. First what we do is that once this VB is made, we extend the language of ZFC, the classical set theory started with, by adding constant symbols corresponding to every element here. So you take a function, suppose you are taking a function f, and then you are naming it, giving a constant symbol to the language corresponding to f. You are taking another function g, you are giving another name, another constant symbol to the adding to the language of ZFC, and so on. So that means you have added names corresponding to every element VB here in the language. Then what? Then from that language we take any sentence and then we'll assign an algebraic value. That means the Boolean algebra we took, every sentence will be assigned to, we'll take any sentence and we'll, by some map, some interpretation function, we will map this sentence to a Boolean value we started with. The Boolean algebra we started with, we'll assign. How we'll assign that? We start with the atomic formulas first. So we say that you take any U and V, U belongs to V. This is an atomic sentence. Atomic formula here is also a sentence. U equal to V is a sentence. And somehow their algebraic interpretations are given. So if you are not familiar with this, you do not have to go enter that what it is, but whatever it is, you just believe me for the timing that we are assigning U belongs to V to some algebraic value. According to that, we are assigning some value to U equal to V for any U and V. Okay, and these are recursive definitions. You see that when we are defining U equal to V, we are using equality from the domain of this V. When we are defining U equal to V, we are using belongingness in the domain of U and V. So recursively we have defined it. So that's all. So for any two elements U and V from that collection, U belongs to V is some Boolean value, U equal to V is some Boolean value. That's all till now. Once it is defined, there is, of course, we can understand that we homomorphically extend this interpretation function to define or to assign Boolean value to every sentences of the language. How? Very simple. Like you take any two sentences, sigma and tau, you take the mean. It is assigned to the Boolean algebra, the Boolean value, the value of sigma, meet the value of tau. Oh, sorry. Yes. So you take the value of sigma here, you take the value of tau here, and you take the meet of the Boolean algebra. That is the value of this sentence, sigma meet tau. And simply it goes like that. If you take the negation sigma, this is simply you take the value of sigma and take the complementation of it, the Boolean complementation, simply. Similarly, we define the quantifiers as well. So for all x phi x is defined how? Like you take all the values of this phi x for every x of VB, you take all these values and you take the infimum of all these values. that is also Boolean value. Why? Because it was a complete Boolean algebra we started with. So any set has infimum, any set has supremum, right? So that infimum is the value here, and for there exist, you take the supremum, that supremum is the value for this there exist function. So that means that in this way, we actually assign Boolean value to every sentences of the language. Okay? Then we say that a sentence of this language is valid in VB, in that class we made just 2 slides before we discussed about it, if the sentence is getting value 1. This way we are assigning. Okay? So till now, I just am saying in like at a glance what we have done till now, that we started with a Boolean algebra, and we say that, look, according to that Boolean algebra, we have made a collection VB. VB is what? It contains some functions. How these functions are made? Okay, we discussed. I'm not going to that again. So VB is a collection of functions. It's a class, proper class. And then for any 2 element you take from VB, what we are doing, we first define what is, suppose U and V you have taken 2 elements, then what is U belongs to V? We have given a way to express the, or to find the value of U belongs to V, which is a value of the Boolean algebra. That's all. You take any 2 elements U and V, we define what is their equality value. Like that means what is U equal to V, we have assigned some Boolean value to that. Depending on these things, what we did, we took any sentences from the language and we defined in that way, homomorphically, some Boolean value to that sentence. Okay? So that means any sentence you take, suppose you are taking for all x, for all y, x belongs to y. That is a sentence of set theory, ZFC. So in that way, you can find that, okay, so if we are starting with this Boolean algebra, then what is the particular value to that sentence? Suppose you are taking a sentence, for all x there exists y, x equal to y. Okay, then you can calculate and find, okay, so if this is the Boolean algebra, then this sentence is getting this value, particularly, okay? Now we are saying, if some sentence is getting value 1, we'll say that that sentence is valid in this Boolean valued model VB, okay? Or in this class VB, we say that some sentence is valid if it is ultimately by in that calculation getting value 1, okay? Till now, any question from the audience or from the online participants? Till now, any question from anyone? 1 is the top of the Boolean algebra, normally we have taken. Okay, if not, then this is the celebrated result here, that which says, doesn't matter that which Boolean algebra you are starting with. Always the axioms of ZFC will get value 1 by that calculation. Doesn't matter which Boolean algebra you are talking about. I mean the complete Boolean algebra. All the axioms of ZFC will always get value 1, which implies that for any complete Boolean algebra, this thing VB becomes or validate all the axioms of ZFC. Okay. And that's why in this way we say that VB is a model of ZFC. Okay. This is called a Boolean valued model of classical set theory. ZFC means what? Like, of course, we all know here, but still, like, for the audience, online audience as well, I know that few students are listening. If you do not know, ZFC is that Zermelo-Fraenkel set theory. C stands for the choice also. So ZFC is the Zermelo-Fraenkel set theory with action of choice. This is, we'll sometimes say it as classical set theory normally. Well, now, what happens? In probably 1978, Grayson actually took this idea and he proved that, look, if you change your Boolean algebra by a hating algebra, so there is a point here. See, that Boolean algebra, we know that is connected to the classical logic, right? The same way, hating algebra is connected to intuitionistic logic. Now, Grayson proved that if you go through the same construction, but instead of taking Boolean algebra, if you take hating algebra, then what was happening? When you took Boolean algebra with all these constructions, you got the model of classical set theory, right? algebra valued model of classical set theory, which is called Boolean valued models. Now Boolean algebra is changed by a hating algebra, where hating algebra is connected to the intuitionistic logic. So it is expected that then if you follow the same steps, then the class you get by VH, now B is changed by H. H is some hating algebra, suppose. This VH should be a model of intuitionistic set theory then. And he proved that yes, this is true. If the Boolean algebra is changed by the complete hating algebra, then whatever complete hating algebra you start with, you can always prove that that can validate all the axioms of intuitionistic Zermelo-Fraenkel set theory, IZF. Okay? From this point, we started our investigation, like what said that all these things started at the time of my PhD, that at that time we actually tried this approach. We took this approach and tried to find some algebras where if we, like Boolean algebra is shifted by hating algebra, we are getting intuitionistic thing. Can we find some algebra which in the place of hating algebra, if we can place, which may produce some paraconsistent logic, then the whole thing the same way could be a model of paraconsistent set theory, right? So the search started in that way. And we tried to find some generalized algebraic structure. So not only one algebra or two algebra, but some general algebraic structure which can produce many algebras, okay, as model, but that can produce some algebra as model which are the models of some paraconsistent logics, and so that the corresponding algebra valued thing will be a model of the paraconsistent set theory. So the search started from that point, and finally what we got, we actually partially succeeded, we should say. How? Like by paraconsistent set theory, we are meaning that the basic logic is a paraconsistent logic, and then the set theoretic axioms are either full ZF or a fragment of ZF. So by that, the whole thing is called, like I'm meaning as the paraconsistent set theory here. Like the way IZF we meant, IZF there, the set theoretic axiom is same as ZF. But the logical axioms are different, which is the intuitionistic logic axioms. Okay. Huh? No, we don't have C there. That's why IZF, not IZFC. Okay. So before going to that, to our search, like let's take few more definitions here. Like we know that if we have some algebra A, which is where this part is a complete distributive lattice, then a filter will be called a designated set. What is a filter? Simply like it's a subset of the lattice which satisfy these conditions, that it doesn't contain 0, but of course it contains 1. If it contains something, then anything above it will be there. And if you have any two elements there, then their meet is also there. So if that happens, then we say that this subset D is a filter, and any filter is a designated set. And of course, like one thing is not written here, that if a filter is a maximal filter, I'm not going to that definition, then it will be called a ultra filter, and in this terminology we'll say that thing as an ultra designated set. Well, now what happens, that construct VA as similar to the Boolean valued models, define an assignment function this, okay, or simply denoted by this. The way, look, we denoted the interpretation functions here, like these functions we took, right? The assignments, that every sentence is assigned to some algebraic value. So I'm saying here that you take any interpretation function, like any assignment, any sentence going to some algebraic value here, from the collection of all the sentences of extended language into A, fix a designated set D of A. Then we say that a sentence phi of the extended language is said to be valid in VA. In Boolean case, what was the definition? If this value, for the sentence if the value of the sentence is 1, right? For Boolean case. Here we are saying any value from the designated set. That is quite acceptable, right? That we use these things several times for these algebraic logic things. Acha. So now, so we have, in this case for validity, we have generalized a bit from 1, like in Boolean case or intuitionistic case, what happened? That if this valuation is 1, then it is valid. Now we are saying if this valuation is inside a designated set, then corresponding to that designated set, the sentence is valid. Many valued things. Yes, 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 of course, of course. Okay? Now, this is a property written, that was needed for the development of the theory. I'm not going inside it. There is a property. It is called BQ phi. BQ phi is some property, so you do not have to go inside. And then we are going to define an algebra which we called a reasonable implication algebra, which has these properties. So look, and this is called a deductive reasonable implication algebra if this property is added to this. Again, I'm not giving much time to this slide. There are some properties which are valid in both the Boolean algebras and Hating algebras as well. Yes, like here in so in Hating case, this is implies and implied by. And here it is only one side, not two sides. And these are, like all these things hold very much in Boolean algebra. So classically you can think that all these things are valid. In Hating algebra also, all these things are valid. We have taken these algebraic properties and we told them as reasonable, deductive reasonable implication algebra. Okay? Which one? This one. Deduction. Like suppose from x and y, z follows, then from x, y arrow, z follows, like this. That's why we took it as deduction. So the name suggested by sir, like that this looks like the deduction thing, right? That dt. Okay. Then we just say that a negation-free fragment means what? Like a formula will be called negation-free if it doesn't contain negation, simply. Like it, in any of its subformulas, you do not have negation. Then a formula is called negation-free. Simple. Like you are writing a formula with the other connectives only. There is no negation you are using. Simple. Okay? But in the connectives, you have a bottom as well. In the language, we have taken. Okay? Zero array connective. Okay. Then, we proved this theorem. In 2015, Sir talked about this paper in his lecture, where we said that if A is a deductive reasonable implication algebra, where you are forming this VA, look, it looks like the Boolean valued thing, right? VB we formed at the first slide. When it was a Boolean algebra, we formed this VB, where it was functions, right? Containing functions, and then it was made using the Boolean algebras. Here, we are starting with an algebra A, which is a deductive reasonable implication algebra, and you form the same class VA. And then we proved if that BQ phi holds, that there was a property called BQ phi, right? I told you that you do not have to go into it much. But if that thing holds, then we can prove that all these axioms will get value 1. What is NFF separation? Look, NFF separation and NFF replacement we have written. Only these two formulas, or these two axioms, are axiom schemas, right? Where we write general formulas, phi. So for each formula phi, we have separation axioms, correct? That you start with a set, like you take a formula, you take a set, and then you can extract a subset using that formula from that set, right? So for each formula, you are getting a separation axiom. So it is valid only when the formula is negation free. It is meaning that. For replacement also, it is meaning the same thing, that NFF replacement is valid instead of the full thing. So that means here the axioms we have written, this collection is not giving you full ZF, but a fragment of ZF, which is a negation free fragment, right? Also, foundation is not here. You see that the regularity axiom. Okay. Yes, of course. No, I'm going to this point. So the point is that, look, A arrow bottom, in classical logic, the negation phi can be replaced by phi arrow bottom, right? Since we have taken bottom in the language, correct? So that means that in classical logic, we can replace any sentence by a negation-free sentence, correct? So that means from this theorem, we can prove that for any complete Boolean algebra, VB validate the full ZF from this theorem itself as a corollary. Why? Because a Boolean algebra is a deductive reasonable implication algebra which satisfies this property, and NFF separation, any formula which we use as separation, it can be replaced by a negation-free fragment by making negation phi as phi arrow bottom. That's why the complete collection of separation axiom could be found as NFF separation in the logic where negation can be replaced by arrow bottom. Where you cannot replace it, then you are not getting the whole thing there. But in Boolean case, you can write it, right? So the whole thing is just a corollary from this theorem that the Boolean valued model is a model of the full ZF, right? Of course, here we do not have foundation, but for foundation, I'm going to the next slide, which says this. Achha, now, the point is, so what was our motto? Our motto was to find an algebra like the Boolean algebra or the Hating algebra. We wanted to find an algebraic structure such that if we follow the same construction, this model will be a model of some non-classical set theory. The non-classical part from where it is coming inside, if this algebra itself is non-classical, so we actually wanted to find paraconsistent models. So if this algebra is a paraconsistent algebra, then probably this VA will form a paraconsistent set theoretic model. Then now our point is that do we have some algebra which is satisfying, which is a deductive reasonable implication algebra, but which is paraconsistent? Okay? If we can find it now, then we have a partial answer. Partial means why I'm saying that, because it is negation-free fragment thing. So not full ZF, but at least we can have a partial answer to our search. And yes, we could find an algebra like that, which is this algebra. I'm not going much into that because it is like a three-valued algebra we found at that point, and then we searched for this mid, join, implication star, all these things, and then finally we proved that if you take D is equal to 1,2, you can prove that PS3 is a deductive reasonable implication algebra. Not only that, the property NFF BQ phi also holds in VPS3. And that means from that theorem we can prove in VPS3, we can prove that all these axioms are valid. Okay? Now, in addition, the thing which was left, the foundation, we can prove that the negation-free fragment of the foundation axiom is also valid in this model, VPS3. Okay? So, VPS3 becomes a model of, algebra-valued model of the negation-free fragment of ZF. And what is the logic of PS3? The logic of PS3 can be proved to be a maximal paraconsistent logic. If you take D is equal to 1,2, PS3 you take, so you can prove that the logic sound and complete with respect to this is a maximal paraconsistent logic. Maximal paraconsistent logic means what? It is a paraconsistent logic. Not only that, it is a subclass of the sublogic of the classical logic. And if you take any formula which is not valid in this logic from the classical part, that means it is a proper subclass of classical logic. If you take something from outside, theory I am saying, and if you are including it inside, then it will be the classical logic itself. Okay, so it's a proper subclass, the logic of PS3 of the classical logic. And if you take some sentence which is not true in this subclass, and you are just including it as an axiom to this subclass, you will get classical logic. If that happens, then we say that the logic is a maximal logic. So we can prove that the logic here, it is a maximal paraconsistent logic. And where we just discussed these things. Acha, here, I just want to mention here, since Walter is also present, so I want to mention after this, that actually by this motivation we found this three-valued algebra PS3, and we proved totally independently that this is paraconsistent logic, and it was also published here. But then when it was like at the verge of publishing at that time, probably in the Fifth World Congress, someone, either Hitoshi or someone else, I don't know, he told me that, look, I think that the same three-valued algebra, like Carnegie and Coniglio, they worked on it, and they proved they found a sound and complete logical system of this algebra. You may go through this paper. And then we went through, and then we found that, yes, the same algebra they took, and they independently, with some different motivation, of course, this is not the set theoretic motivation, they proved their sound and completeness. But at the same time, this paper was accepted in the proceedings here, and then this was also published, our proof of the soundness and completeness of this three-valued thing. But the motivations of them and our motivation are totally different. But this particular three-valued thing was studied in two different times, two different ways, in two different continents, of course. Well, so let's go ahead. So what till now we have found? We have ultimately found some algebra which can produce a paraconsistent logic, and that has the power that if you make a algebra valued model on that, following the Boolean valued case, it validates a negation-free fragment of ZF. Okay? Well, that means we already have BPS3 as an algebra valued model of a paraconsistent set theory. So before this, I think that in the literature, we did not have any algebra valued models or the models of paraconsistent set theory in this approach. So probably this was the first work where we can find the approach of paraconsistent set theoretic models in this way, in the algebra valued model way. Well, after that, there are a lot of study went on, and still people are working here. I'm also working. So what happened after that? You see that extension of PS3. Now, here Giorgio and Santiago, they took up this project, and then what they proved. So PS3 was, that three-valued thing was a three-valued linear algebra. What they proved, now they took in Santiago's PhD thesis, and they proved that not only this three-valued linear thing, if you take any ordinal number, suppose, it's a totally ordered algebra you take, any totally ordered algebra, okay, so finite, infinite doesn't matter, and then if the implication is defined like this, where 1 is the top element and 0 is the bottom element, okay, then, so it's a linear algebra where implication is like that. And mid join, of course, linear means you can understand. Join goes to the max, mean goes to the mean, like the normal linear thing, okay. Then what happens? We can prove this thing. For any totally ordered implicative algebra A and any designated set D, this validate the negation-free fragment of ZF. So which was closed or bounded in my thesis by three-valued algebra, three-valued linear thing. In Santiago's PhD thesis, they extended it to any totally ordered thing. Okay? Yes. Boolean value and kind of that linear thing, yes, of course. So our was that for any generalized algebra valued, reasonable implication algebra, we have this, and they proved that all these algebras are reasonable implication, and then with that implication, and then a few more things that BQ5 holds, and that's why this holds there. Not only that, they introduced complementation in this way, in two ways. These are the two ways. Like one way is that if the negation of 1 goes to 0, 0's negation goes to 1, and anything else inside its negation is itself. If this is one way you define, and if your D, the designated set, is not equal to the top element only, then you can prove that any totally ordered thing is a paraconsistent algebra. Like its logic will produce a paraconsistent logic. Of course, right? You take anything from the designated set which is not 1, then its negation is itself. It remains in the designated set, right? So anything from the designated set which is true, its negation is the same element if it is not 1, which remains in the designated set. So an element and its negation both are true. 10 minutes. Okay, I'll finish. So that will give you a paraconsistent logic. Its logic will be paraconsistent in that way. If you take the negation in this way, that 0's negation goes to 1, and 1's negation goes to 0, anything else negation goes to 0, then you get this result. This is crazy. You see that this is not anymore the negation free fragment. This is a full ZF now. If the negation is defined like this, the 0's negation goes to 1 and anything else goes to 0. No. That is our point, that you do not have to believe on the standard classical thing to get ZF. So ZF could be found in different ways. We have already proved it. So ZF is not a property of the classical thing now, like what we have proved till now. The ZF, if you take the syntactic expressions, the same way we use in the classical case. So that is not classical anymore. Like you can get it in any different way. We have proved it till now. So this is one of them. Okay, and then I told you that okay, we found all these algebraic valued models, blah blah blah, many things you have said. But then what? Getting models of paraconsistent set theories. But then what? Which kind of mathematics we are getting inside in those models? Like, are there some reasonable things we are getting, or like non-reasonable things we are getting? What we are getting? We worked on this and found some beautiful results, which I'm just showing you. That suppose from the totally ordered algebras we took, now I am eliminating few elements from there. Like I'm taking not all the totally ordered thing, but well-ordered thing. Okay, that's all. Okay, well-ordered thing. Okay, if that is the case, and then the implication is defined the same way the totally ordered implication was defined, then what happens? That suppose once we define it, and we are defining the negation like this, you see that what is the big scope of negation we have? I'm only saying 0 goes to 1 and 1 goes to 0. What the middle elements are going where, we are not defining. Anything it could be. 0 goes to 1, 1 goes to 0. That's all. The middle thing could be anything. Okay? They could be itself, they could go to 0, they could go to 1, or anything it could be. If that is the case, then we say that an algebra like that is called a PS algebra. This name PS also came from that PS3. So it is somehow generated, all the studies started from that PS3 thing, right? So we talked, or we called those algebras as PS algebras. And then what we got, depending on the negation you define, the algebra could be paraconsistent, it could be paracomplete, it could neither be paraconsistent nor be paracomplete, but some non-classical thing. So now you see that we are going beyond paraconsistency as also, depending on the negation, because we kept the negation part open, right? We said only 0 goes to 1, 1 goes to 0. Now it is proved in the paper itself that depending on the definition of this negation, the logic of these algebras will be maybe paraconsistent, maybe paracomplete, or neither of them. Then what happens? We can prove that for all those PS algebras, it becomes a model of the negation-free fragment of ZF. And then what? What actually validate there? See, for any PS algebra, this here in this model, mathematical induction is true. Believe me that recently we have proved not only mathematical induction, these present results are not published yet, but the transfinite induction is valid as well. So, 5 minutes, okay. And then, what are the other things like action of choice? You see that we say, if in the ground model action of choice is valid, for any that kind of PS algebra valued models, action of choice is valid. Not only that, Cantor's theorem and Schroeder-Bernstein theorem. Cantor's theorem says what? Like, okay, so these two theorems you see, Cantor's theorem means that any set you take, its power set has greater cardinality, right? Schroeder-Bernstein theorem is what? Like if you have two sets and you have injective function from one set to another and this set to that, then their cardinalities are same. All these things holds there. Think about it. They are actually paraconsistent set theory or paracomplete set theory or neither paraconsistent nor paracomplete, but still all these things are valid inside, like the classical mathematics. Not only that, look at this. This is also a crazy result. Generalized continuum hypothesis. It's an if and only if thing. If in the ground model it holds in the algebra valued model. If in the algebra valued models, general continuum hypothesis hold, in the ground model you know that in the ground model it is valid, otherwise it cannot be. So it's a characterization. Not only that, I did not write the other results here, but believe me, all the like basic cardinal arithmetic, every property hold. Like the cardinal addition, cardinal multiplication, cardinal exponentiation, everything hold as it is, they are in the classical case. Okay, in these non-classical models. So this is actually a very, like I should say that the maximum existing paraconsistent set theoretic models, they will differ here very much with these paraconsistent models because they are like, you see that there are some other results also, like suppose Russell's set. So Russell's set is a set in the existing maximum paraconsistent set theoretic model which we have in the literature. But here, Russell's set is not a set, is a like the normal way classical set theory, we see Russell's set, the same thing happens here. So it becomes a class. Collection of all sets is not a set here, it's a class. Collection of all ordinal numbers, it's of course almost like the classical things happening inside, though it's a model of paraconsistent set theory or some other non-classical set theory. Well, so I'm not spending much time here, but this independence result, I'm not going. Georgie will take care of that in the next talk. But just before I finish, I want to talk about one more result, that though we have many things, but we have a drawback in all the in this entire study here. Though I can remember that Professor Chakraborty sir, he told me once that why you are telling it drawback. So it's a different way of seeing things. So if you think it is a drawback, it's a drawback, but I don't think it's a drawback. But anyway, we have written it. People like to take it as true, but it's not happening in our model. What is that? The Leibniz law of indiscernibility of identicals, which we say that whenever you have two sets x and y, and you have some property phi, like some formula, and for x the property is valid, then for y also the property is valid, right? So this is the Leibniz law of indiscernibility of identicals. But the point is, this thing fails in all these models. Okay. Yeah, okay. So, well, so we leave this thing for discussion. No, this we have written in the syntax. Double arrow for the algebra. This is for the syntactic connectives. Okay, that is a language connective. Okay, and double arrow we used for the algebra, interpretation, semantics. Achha. So, but the point is that who knows? Like maybe yes, yeah, 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 yes. And then I just want to finish, Shankara, if you give me two more minutes. We actually fixed, if it is a drawback, we fixed this drawback by changing the interpretation function. What is that? You forget about all, okay, so we talked about some other algebra, co-bounded algebra. What is that? I'm not going to this. But on that algebra, we fixed this interpretation function. We changed the interpretation function by this way. Look, I just forget about it. What is written? Belongingness, it is same what for the Boolean case we have taken. But as you have pointed out correctly, that the equality is different, we made some change in the interpretation of equality. What we did? We just kept the normal thing which we had in the classical case, but we have added the contrapositive statement of it as well. So we are saying, look, x equal to y means what? In classical set theory, we say that x equal to y means anything in x that is also in y, and anything in y that is also in x, right? We have added two more things. What are that? Anything which is not in x, which is not in y, and anything which is not in y, that is not in x as well. We have just added this thing, which looks more classical, right, than the actual classical thing. Of course, in Boolean case, that is equivalent to the normal one, but we have just added it here. Look, the contrapositive thing here, and the contrapositive thing here, right? And what we got? Massive. The only from ZF we have changed the extensionality axiom by the way I have just discussed. Extensionality axiom says what? If this holds, then x equal to y, right? We have added this thing. If x doesn't contain something that is not in y, y doesn't contain something that is not in x. So, okay? You take these two things, take the conjunction, and that is implies x equal to y. We have taken this extensionality bar, and we proved this, that forget about all these things, but just see that if you take this interpretation and you take the co-bounded algebra, then the algebra valued models with this interpretation validate full ZF bar, not the negation free fragment. And together with the Leibniz law of indiscernibility of articles. So there is no drawback, nothing, the full ZF we are getting with non-classical models of set theory. Right. Right. But still keeping the whole thing as paraconsistent set theoretic model or paracomplete set theoretic model or neither paraconsistent nor paracomplete anything. So it's not only classical models. So it is giving like at the background is a total non-classical, but at the front you are getting the whole the classical ZF things. Okay. So this is recently published here in 2024. So we three worked on this, Santiago, me, and Giorgio. And thank you. Any question? Any question?
Any questions from the online participants mainly, because offline we are going to have tea and we can ask our questions there. Walter, I see that you unmuted yourself. Do you have a question or a comment?
Well, just a comment. Of course, we have. I mean, there's something very nice happening. So there are two kinds of models. Marcelo and I are working on one line. Giorgio, you, and even Chakraborty are working on another line. It would be very much interesting if you could solve the problem in two ways. either we could show that there are two completely inherently different models, or they are more or less the same, and it's something missing, like a bigger picture, so that our both approaches are particular cases. So any answer to this basic question would be very much interesting according to my view. So that's only something I would like to say. I think that either our models, Marcelo, Cornelia, and myself, are not finished, are not ready, and I see that your models are also not perfect in all possibilities, right? So that's my feeling. Maybe I'm wrong.
Okay, I'll keep in touch, and I'll talk to you regarding this via mail, I think, and so that we can discuss in a more expressive way, and then we'll see that how much we can do. Okay?
Sure.
Okay.
I think you got my point of view. So either they are inherently distinct approach, and that would be very nice, because then we have more models than we are thinking about, or they are basically the same models regarded from different perspectives. I cannot decide in which side we are.
Definitely, I can say that these are not the same models. Depending on these interpretation functions which were changed, the models, you see that the Leibniz law is valid here. So the models are now looked very different. Like I'm saying that in according to the interpretation, the models are much different than our model itself, which we did before, like with the normal Boolean interpretation function. And also, like, if you take the co-bounded algebra kind of thing, the models are different, because as I've said, that few models are giving rise to the paraconsistent set theory, few models are giving rise to the paracomplete set theory, few models are neither paraconsistent nor paracomplete. So the models are really not same. So, but of course you are true that we believe that we are again like we are fetching stones on the beach. That's true. That there are too much thing left which we cannot see even. Too much things left, and you see that the whole mathematics is left inside. That what will happen inside, like what is the topological structure, what is the real analytic structure, what is the algebraic structures, what are the everything is left inside. So we don't know that what is going to happen, and see that these models are not differing with classical set theory from the basic level, but they are differing in the abstract level. So our daily life mathematics is not hampered by these models.
But you know, we are also interestingly enough, we are also having some difficulties with Leibniz law, which reminds me of Nagarjuna. Perhaps Nagarjuna is completely right, and we are sort of rediscovering again something that's very old. That identity is not what we think it is.
Okay, yes, I got you. But I think that we should discuss this later as well, and then maybe something come up. Okay?
Yes, with much pleasure. We'd be very pleased to discuss with you.
Okay.
Anytime you feel free after this conference, of course, would be very much happy to discuss that.
Okay. Thank you.
Giorgio and Chakraborty as well, and other people.
Thank you, Cornel. Thank you.
Okay. Thank you for your presentation.
Yeah. Thank you.
Okay, so if there are no further questions, we will take a short break. This is more for the online participants. Giorgio, I know you have already joined and your talk was supposed to start 10 minutes ago, but we still need to have a 10-minute break and then we'll start after that. Is that fine with you, Giorgio?
Sure, perfect for me.
Okay, great. All right, so we break for 10 minutes. Okay, so we are back. People online, if you can hear me, please somebody let us know.
We can hear you.
Okay, great. So it's my pleasure to introduce Giorgio Venturi, who's going to speak from Brazil now, if I am not mistaken. But he's a professor at the Department of Philosophy at the University of Pisa, and he's an expert on mathematics and philosophy both. So over to you, Giorgio.
Thank you very much. Let me try to share my slides. Can you see them? Let me. Where is it? Can you see my slides? No. I can't hear you. Can you see my slides?
Yes.
Okay. So I won't be able to see you. So if you have any question or if you want to tell me something, just shout.
Giorgio,
So,
just give us 2 minutes. We need to do something over here so that your slides get full focus.
Okay, no problem. If it's better, I can send them to you by email and you can share them, if it's better for you guys.
No, I think, Giorgio, we have done it.
Okay, good. So can I start?
No, but no. স্পটলাইটে তো করলাম আমরা। আচ্ছা, ও বলছে যে ও পাঠিয়ে দিতে পারে, তাহলে আমরা এটাকে এখান থেকে কন্ট্রোল করতে পারি, সেটাই করবে। আমরা ইয়ে করবো, ওখানে বলছি করবো না, ঠিক আছে। Okay, Giorgio.
Giorgio,
Yeah.
you can carry on.
Okay, thanks. So first of all, I'd like to thank the organizer for the invitation, and especially Sharaf, with whom I've been working in the last 5 years or so. And it's been a pleasure to work with him and to know better the Indian community. So, well, thanks again. And let me start. It's a continuation of Sharaf's talk. And this time I will talk about independence in non-classical theory, especially because what Sharaf presented is the construction of all these algebraic models, which, at least in the classical sides, are used to prove independence in set theory, in the classical set theory. So as soon as we manage to build all these different models of paraconsistent and paracompletism, I mean, in general, non-classical set theories, the first idea was to try to apply them, as in the classical case, to independence, especially because when you have two models, you can try to prove the independence of some sentence. So in general, the talk will be to prove independence, as I said, in non-classical set theory. And the method we will use is, of course, that of algebra-valued models, but specifically, we will use a product construction of algebra-valued models, which is built on top of a product construction of algebras. So it is slightly different than the normal use of iteration in in the forcing technique, but it's related to that. So, and the outcome of all this work will be that the phenomenon of independence, at least in this non-classical case, is a bit trickier than the classical case, exactly because there are a few things to be handled with care, let's say, but we'll see in a moment. So, okay, so the table of content of the talk is I'll just in one slide introduce the notion of independence, and then I'll give you the construction of the product of algebras that will lead us to the product of algebra-valued models. And then I'll give you some of the main results, which are some general results about independence in non-classical set theory. Because the bottom line, I'll show you the theorem in a moment, is that we can import all classical results in classical set theory to the non-classical case. And then we will end with some philosophical considerations about, in some sense, pluralism in set theory and in mathematics in general, pluralism with respect to the logic we use for these theories. And these things are now being investigated more carefully, the technical but also the philosophical aspect of all this independence phenomenon in non-classical set theory by Santiago Djokovic, who's now working in Brazil. Now let's start with independence. So again, in some sense, Boolean valued models are, and algebra valued model in this case, are forcing. But forcing is the best technique we have to prove independence, but it's slightly complicated, especially on the technical side when we use a countable transitive model. But luckily we have an equivalent, more intuitive version of it that uses Boolean valued models. So the idea, just to give you, I don't have a blackboard there, but the idea is that we have the universal sets, which is normally V, and within V we build some smaller inner models, which are models of some different theories extending CFC. So the idea is to try to do the same, building these inner models within V, which are non-classical and which can be used to show independence in non-classical set theory. The reason I use the hands in this way is because there is this classical V-shaped form of V, and we can view this construction as building an V inside a V, meaning a model inside a model of non-classical set theory within the classical model, which is the classical universal sets. As we will see in the end, this can also be disputed, the primacy of what comes first between classical and classical, but we'll get that in a moment. So let's start with the product of algebras. Now, the idea is very simple here. So we take two algebras in the same signature so that we can compare the operations. Let's call it A and B. And then we just take the product, the Cartesian product of the domains. And then we can extend in an obvious way the operations pointwise, meaning that if we have a capital AB in this product algebra, and we have a capital CD, the joint of them is just that the capital, which consists of the joint on the first component of the first and the first component of the second, with respect to the first algebra, meaning A joint C with respect to the joint of A, and the second component is exactly the same on the second components, meaning B meet D with respect to the meet of B. So in this way, we can pointwise extend the operations on A and B and get a new algebra with new operations, whose domain again is the Cartesian product of A and B. Now, this definition of the product of algebra allows you to extend a lot of nice properties of the algebras, like, for example, the possibility of defining an order between the elements. As we can define an order between the elements of A and B, we can define an order between the couples of A cross B. Again, defining it pointwise. So AB is less than CD if A is less than C with respect to the order of A, and the same for B. And what is also interesting, which will be essential for the construction we have, is that the completeness of the two algebras A and B transfers to the completeness of the product of A and B. So we can actually use A cross B, the product of A and B, to interpret existential and universal quantifiers, which are can be interpreted just because of the completeness of the corresponding algebras. Okay, so now that we have a product algebra, we want to use this product algebra A cross B to define an algebra-valued model on this product. But if we want to do that, we also want to define validity in this new structure. So the idea is that we get to the definition and I'll read it in a moment, but the idea is that we have a designated set, which is the set of truth value for one algebra. We have the designated set for the second algebra, and we just take the product. So a formula receives the designated value in the product of the algebras, when pointwise is received a designated value for with respect to the first component, which needs then to belong to the designated set of the first algebra, and the same for the second. So for any two algebras A and B and a formula, the validity on the product is defined with respect to the designated set of A cross B, which is the Cartesian product of the designated set of A and the designated set of B. Okay, and given this definition, we can prove a decomposition theorem, which seems obvious, but it's not obvious at all, which tells us that the validity as calculated with respect to this algebra, meaning we inductively define the validity with respect to the formula, with respect to the truth values in A cross B, is an element in the product algebra, and the couple of which is this element, so the first component of this couple and the second component of the couple, is exactly phi as calculated with respect to A and phi as calculated with respect to B. So just a small technical comment on this. Notice here that also the reason why this theorem is not obvious is that this phi here is normally in algebra-valued construction, we extend the language with constants for every element of the algebra-valued model we construct. So this phi here, the first evaluated in A cross B, is in the language where we have constants for all the A cross B elements, which are different from the VA elements, which appear in this evaluation, and the B elements, VB elements, which appear in this evaluation here. So there is an induction when you have to be careful to project a formula and a language in one side and the other side, but we finally get this result here. Why is important this decomposition theorem? Well, because it tells us exactly what is true in the product algebra. So again, let's use the decomposition theorem and plug it into the definition of validity. So the validity of the formula in VA cross B is the couple validity of A, validity of B, which is of course an element of D of A cross D of B, which is an element of D of A cross B. Now, the fact that V of A belongs to D of A, meaning that when we evaluate phi with respect to the algebra A, we get into the designated set of A, it's just another way to say that phi is valid in D of A with respect to this filter here, the designated set. And the same actually holds for B. Now, this means that when you evaluate the formula, we here just forget about the designated set, but when we evaluate the formula in V of A cross B, this is equivalent to say that the formula needs to be valid in V of A and in V of B, which is if a formula phi is valid in the product algebra construction, it is because, and only if, it is valid in V of A, in the algebraic model built using A, and in the algebraic model using B. So what we are getting in model theoretic terms is the theory of V of A cross B, meaning the formulas that are valid in V A cross B, is exactly the intersection of the theory of V of A and the theory of V of B. So the decomposition theorem actually tells us that when we build the product construction, what we get is an algebraic model that validates what is both true in V of A and in V of B. And this is very important because in some sense, we're actually taking just the intersection of the two models. And if we have that V of A validates some fragment of V of CFC, and the same holds for V of B, this will still holds for V of A cross B. Okay, so now just to give an example, let's consider the deductive reasonable implication that have been introduced by Sharaf. So as you remember, these conditions were sufficient condition for the validity of the negation-free fragment of CF. So the fragment of CF without negations. So we don't have negation in the fragments. So the theorem we can show here is that if two algebra A and B are deductively reasonable implicant algebras, also such that BQ phi holds for a formula phi in V of A and V of B, then again, just a direct application of the decomposition theorem, we have that BQ phi holds in V A cross B. Exactly because if it holds in both, it will hold in the product. But also, so this means by what Sharaf proved that this is enough to show the negation-free fragment holds in NFF in V A cross B. But also we can prove that the product algebra is still deductive reasonable implicative. And so in some sense, we can iterate the process. So we start with RIA, we take the product with the RIA, we get something that still validates CFC, and which is still a RIA. So we can take the product with another RIA and so on and so forth. Another interesting application is with the last models that Sharaf presented, the one that are using the PA interpretation function. Interestingly, I mean, just a comment on that to complement what Sharaf said, the construction of the models using this interpretation function is exactly the same construction we have using the standard interpretation function, which is the one we use in the Boolean valued case. So what changes here is not the ontology of the models we consider, but just the interpretation of them. So the interpretation of the formula that talks about the same ontology. So in some sense, we are just changing the interpretation of the formulas in order to get CFC valid. We're not, in some sense, modifying the underlying ontology. We are just viewing sets of these algebra valued models in different ways, but in such a way that we actually get the validity of full ZF, actually full ZFC in this case. This is something I'm not sure it's been published, but we can actually, using the PA assignment function, talk about CFC. So in this sense, these models are completely different from what we had before because we are actually seeing things in a different way. So that was the interpretation function that added just the contrapositive of equality in the interpretation of the formulas and the interpretation function that allowed us to show the validity of full CFC in these models. But interestingly enough, all the things we did so far with understanding what is the interpretation of the product of formulas of algebras and the decomposition theorem and everything that is connected to that can be transposed to this new interpretation function, exactly because, remember here, when we stated the decomposition theorem, it is stated with respect to this interpretation function here. But now we have to kind of reprove it for this new interpretation function, but this is possible and it yields the same results. So the interpretation of a formula in the product gives a value in the designated set of the product of the two designated set of A and B, which is exactly the pair consisting of the value of phi with respect to the A with the algebra A and the value of phi with respect to the interpretation in the algebra B. And again, this means that when we evaluate with the PA interpretation function a formula in V of A cross B, we're just taking the intersection of V of A and V of B. And so again, if we have that V of A in which when we use this interpretation function, we get the validity of all the ZFC axioms, and the V of B having the same property, meaning that using this interpretation function, we get the validity of full ZFC axiom, maybe something more. Then in the product, we still have the validity of ZFC axiom. So this is important exactly because, again, when we use algebra valued models or forcing to prove independence theorems, we start with the model of ZFC, we produce another model of ZFC, and a third model of ZFC showing the independence of a formula. So you have a model of ZFC where when a formula holds, another model of ZFC when this formula doesn't hold, and we use it to show independence. But this tells us that the product construction actually allows it to preserve ZFC axioms, and this is enough then for proving independence. Okay, now let's get to the main results. So again, the main theorem is that all classical independence results are preserved in this context. So just as a piece of notation, we, because of the separation between non-logical axiom and logic, we define BZF as a collection of logical and non-logical axiom of classical set theory, while we keep BZF only for the non-logical axiom. So BZF is what we normally call ZF, because B stands for Boolean, while ZF is just the non-logical axiom. So the ZF axiom without all the axiom for first-order logic, first-order classical logic. So let's read the theorem and comment on that. Suppose phi in the language of set theory, the normal language of set theory, with just the belongingness as a non-logical suit. Suppose phi is an independent sentence with respect to BC. So think about CH, for example. So phi is a sentence which is independent from classical set theory. And suppose that A is a complete algebra whose corresponding logic is possibly a fragment of CPL. So we can think of PS3, as in the case of Sharaf presented. So we have a sentence which is independent in the classical case, and an algebra which gives us a model for a logic, a ZFC with the non-classical logic. And suppose that when we do the construction of V of A using this non-classical algebra here, we get that a fragment, or possibly all, a fragment of BZF. So we get a fragment of the logical part and of the non-logical part, exactly because we might actually get just a fragment of the non-logical, as in the case of PS3, which is a maximal paraconsistent logic, together with all ZF axioms, for example. Then if we can show the validity of phi in V of A, which again, here validity means simply that phi is consistent with this set theory here, expressed in V of A. Then there are two algebra valued models of T, which is the theory, the non-classical set theory, which are two algebra valued models of the non-classical set theory, which are not of the classical set theory, which do not agree on the truth value of phi. Meaning that, again, think about this as we have a sentence phi, which is independent in the classical case. We have an algebra model built using non-classical logic, which is consistent with this phi. Then we can show that this phi is actually independent from the non-classical set theory, which holds in V of A. Okay? So in a moment, we'll give you a concrete example using the example of CH, the continuum hypothesis. But in general, this theorem tells us that if we have an independence phenomenon in the classical case, we can extend it directly to the non-classical case. Now, just a comment on this. So if you think there is a way of thinking about independence from the classical case to the non-classical case in a trivial way, which is not the one expressed by the theory. Because if you think of two models of classical set theory, okay, which show the independence of phi, then these two models of classical set theory, meaning that you have full ZFC and full classical logic, these are models also of weaker theories in the sense of fragments of classical logic or fragments of set theory. So in themselves, two classical models also show the independence of phi in the non-classical context, because they are models of non-classical logic plus something else. That else, they make them classical. But what this theorem is showing is that we can actually build two models which are not like these. These are models of the weaker set theory and of the weaker logic. So in some sense, what this theorem is showing is that we can perform the independence result of the classical case in the non-classical case. So without the limited means of non-classical set theory, we can prove the independence of phi. Okay? So let's go on to the next general results about independence in the non-classical case. Because I mean, as we said so far, all classical independence results actually can be proved in the non-classical case. But the question is, are there other non-classical independence phenomenon which do not appear in the classical case? The answer, of course, is yes, because the lower the logic, I mean, the weaker the logic, of course, the more independence phenomenon you will get. So this is to say that there are sentences that we do not, that were not independent in classical set theory, but that now cannot be decided, which become independent in this non-classical case. So in order to define independence with respect to what, let's define these, what are the set theories we are considering here? Because again, in what Sharaf presented in so far, and we still haven't talked about specific axiomatic non-classical set theories. We are talking about the theory of some models which are non-classical. So our approach is completely semantic. We consider models which validate fragments of CF, but we are not axiomatizing these non-classical set theories, which is something that can be done in principle. We're not sure, but this is not what we did so far. So, but we can still define completely semantically a notion of theory, which is the theory which is common to all these models we construct with this product construction. So concretely, let A be a complete algebra whose corresponding logic is contained in CPL, classical propositional logic. So we have a non-classical algebra. Then we define AZF to be the fragment of classical ZF, which is valid in all models of the form B A cross B. So we take V of A and we take the product with B, and we make B range on all possible Boolean algebras, and we consider what remains true in all these models. So this is kind of the minimal non-classical set theory we are working with, modulo all the independence phenomena, which is exactly what happens in ZFC. So we have a lot of different independence phenomenon, but when you intersect all Boolean valued models, you get ZFC. Possibly something more, because there are things that are absolute, like arithmetical statements that cannot be changed by forcing, but I mean, mainly you get ZFC as your basic set theory. So the theorem says that if phi is a sentence, which is valid in B of A, meaning it's consistent with the set theory of AZF, and BZF actually proves that the negation of this formula, so this is something that classical set theory says it's false, then phi becomes independent with respect to the weaker set theory with this AZF, which is what we get as non-classical set theory modulo the independence phenomenon, which is independent from AZF, but of course not from BZF, because I mean it's proved to be false, so it's not independent. Just to give an example of this, so consider an example with respect to the theory PZF, which is what is common to VPS3 when you take PS3 with the product with all possible Boolean algebras. Okay, so with respect to in some sense, it is semantically the semantic definition of the set theory of PS3. So in this PZF, we have that this formula holds, which is in some sense saying expressing the paraconsistency of PZF, because it says that there are two sets, X and Y, which are equal, but for which one element Z belongs to X, but not belongs to Y. Okay, so this is compatible with extensionality, just because we're in a paraconsistent setting. So we have extensionality holds, but we don't have that the negation of this formula holds, which should be the case in the classical theory. So in the classical set theory in classical ZFC, this is just false because of extensionality. But in PZF, even if we have extensionality, still this formula holds, actually holds and not holds, because it's paraconsistent. So this gets value 1/2, which means that it's valid and not valid the same. So the application of the previous theorem in this case that says that if A is a paraconsistent algebra, meaning that there is a sentence that is both true and false in P of A, and phi is negatively decided in classical set theory, then phi becomes independent in AZF, in this case PCF. Okay, just a comment on the independence here that I kind of hide under the carpets. So notice that given the possibility of non-standard behavior negation, we define independence of phi as the existence of two structures such that one models phi while the other do not model phi, which is not necessarily equivalent to validating not phi. So in this case here, this phi in itself become independent because it's negatively decided. But this is not in general true for every non-classical sentences, because paraconsistent sentences, if they're not negatively decided by the classical CFC. Because the idea here is that validity and not validity, which is normally traced by but in the negation, in the classical case, needs to be understood in semantical terms. So validity is V of A validating phi, and non-validity is V of A not validating phi. Okay, this is the notion of independence we work with. Okay, so let's give the concrete example of the independence of CH. The idea, I'll just give you, I'll not go through all the details of these construction, but just to give you an idea. So let's consider a case of PS3, okay? The idea is that in order to prove the independence of CH, we first need to know that CH in this non-classical context actually means what we want this to mean, meaning that the 2 to the aleph 0 is actually aleph 1. So there's no infinite cardinals in between alephs, I mean the cardinality of the natural numbers and the cardinality of the real numbers, okay? So the cardinality of the real numbers is just the first uncountable cardinal. But in order to make CH mean the same thing in this non-classical context, we need to develop the notion of ordinal and cardinal and bijection, because it's all we need to define cardinality. But in order to do that, we have to develop all these notions and check that these notions actually have the same meaning also in this non-classical context. So in order to do that, we can, first of all, define an equivalent relation in the elements of VPS3, which corresponds to equality as provided by our model. Because one thing is what our model says, and one thing is how the semantic is behaving. Exactly because all these models behave as we want them to behave only because of the interpretation function we give on the elements of its domain. So we have our ontology, we interpret them, the formulas about this ontology in such a way to validate all CFC, but then we want to have not too a big mismatch between what the model says and what the ontology actually says, okay? So if two sets are proved to be equals in VPS3, I mean, it's, the model validates this U equals V, then we define an equivalent a relation between them, which is an equivalent relation. And then we define a subset of the domain of U, which is composed of the elements in the domain which are actually mapped in the designated set of VPS3. So we take the elements of the domain of U which are relevant when we say something true about sets in VPS3. And we take a partition of this domain of U by this equivalence relation. So what's happening here is that we are considering only the elements of a set in VPS3 which are relevant for saying something truthful about them, and we take partition module equivalence in the semantic sense, which actually corresponds to the syntactic one expressed by the set theory we are reporting. Okay. Now, interestingly, this is enough to say that if for any two elements U and V, if there is a bijection between these partition of the domain of U we defined, then this is trapped in the syntactic side in terms of existing of a function which is a bijection between U and V. So this formula here, there's a F which is a bijection between U and V, is something we can express syntactically in the language we're using. And this lemma, these are results by Sharaf, this lemma says that what actually this sentence says, that there is a bijection between U and V, is actually tracked on the semantic side by saying that there is a bijection between the partition module of the equivalence relation of the elements of the domain of U, which are in some sense truthful. Okay. Now, using this, we can also define a notion. I mean, we can also define a notion of ordinal-like element. I will not go into these details, but this is enough to say that, again, we have a perfect correspondence between what our model says about something being an ordinal, which is validating the formula expressing that this set is an ordinal whose elements are ordinals and it's well ordered by the epsilon relation and so on and so forth. So whether it's normally taken to be ordinal, an ordinal, in the syntactic form as in the Boolean valued case, this corresponds to be ordinal in the sense defined in the semantics, which is this sense here. Okay? And this notion of ordinal-like element is enough to define the cardinality of a set, meaning that this is an interesting theorem by Schraff. Let U be an element of VPS3 and kappa be a cardinal. This kappa is a cardinal in V, in the classical sense, because these let kappa be the cardinality of this set here, the partition of the domain of D of U. This is a set in V. So we are here in the semantic side. So this is a set and it has a cardinality by the axiom of choice in V. Then in VPS3, there exists a bijection between U and the kappa-like element, which is what in VPS3 behave like a cardinal. An ordinal, such that there does not exist any bijection between U and any alpha-like element or any A less than kappa in V. So this means that given a set U, and if we calculate the cardinality of the partition of the domain D of U modulo the equivalence relation, and this has cardinality kappa, then U is in a bijection with a kappa-like element, which is a cardinal in VPS3. So for any U element of VPS3, its cardinality, as calculated in VPS3, is any kappa-like element such that the partition of this guy here in V has cardinality kappa. So again, when we talk about cardinality in V being kappa is what we normally have in set theory, because we're actually working in V, because the construction of VPS3 is a construction we make in V, the universe of all sets, the classical universe, okay? But this set here is what tracks the cardinality according to VPS3 with respect to the notion of cardinal and ordinal number, which is something that corresponds to what we express by being ordinal and cardinal in the classical case. Okay, so again, using this, we can define a notion of canonical representative for cardinals, and as in the Czech names or in the Forcing construction. And then we have that we know exactly what Aleph 0 Czech is, that is the canonical representative of Aleph 0 in VPS3. We know what 2 to the Aleph 0 Czech is, and we know what Aleph 1 Czech is. So we know that when we say 2 to the Aleph 0 equals Aleph 1, this is exactly saying that 2 to the Aleph 0 equals Aleph 1 in the classical case, I mean, in the classical interpretation of these formulas. And the theorem that is a theorem that also appeared in Schraff's talk in the general case of GCH, that if V is a model of ZF such that V validates CH, then VPS3 also validates CH. Actually, this is a if and only. So this is the reason for presenting these terms, that this is in some sense a preservation theorem. So if we have the CH holds V, when we do the algebra valued construction using PS3, then it will also holds CH in that one. But now we have everything we need for the independence of CH. So suppose V is a model of ZF, or ZFC in this case, such that V equals CH. So we have a model of CH in the classical case. And let's have B1, B2, two Boolean algebra such that one allows us to construct the Boolean valued models with CH and one with not CH. Okay, so let V be whatever we want. One is a coin extension where we add a lot of coin reals so that we well, notice that when we consider the algebra obtained by PS3 cross B1 and PS3 cross B2, this is a hybrid, we get, using this set, corresponding to set, the logic corresponding to this algebra is PS3. So we are in the non-classical. Now, by definition of PZF, we have the VPS3 cross B1 validates PZF, because this is what is common to PS3 cross B for any Boolean algebra B. So in particular will be valid here and in VPS3 cross B2. But then again, we have the decomposition theorem. Remember that V is a model of CH. So when we have VPS3 by the previous theorem, in VPS3 we will have CH. But in also VP1 we have CH, and so in the product we still have CH. On the other hand, in VPS3 CH holds, again by the previous theorem on the preservation of CH from V to VPS3. But also in VP2 CH doesn't hold. And as long as the product actually capture what is true in both, it will be enough for one side of the product to not validate CH to actually not having CH in the product, the resulting product. Then we have that these models here are models that shows the independence of CH, or model of the PZF, meaning of the non-classical set theory, and they correspond to non-classical logic. So this shows the independence of CH from non-classical set theory. Okay. In the last few minutes I have, let me just give you some philosophical discussion on this, because this is very interesting, because we're actually extending the notion of independence to the non-classical case. So the multiverse is normally defined as a collection of possibly all models of classical set theory, CFC. So the multiverse, the classical multiverse, is all possible models we can construct, for example, by forcing. Okay. But now we have new models of CFC, but in the non-classical case. But now, what should we do of these models whose underlying logic is non-classical? Well, the question then becomes, are non-classical models of CFC part of this multiverse? Notice that if we include these new models to the previous one we have from Boolean valued models, then we have more models. But when it gets to independence, more models means more independent phenomenon, as actually we showed, which is the case. So if we extend the multiverse of classical models with non-classical models of CFC. And the reason for including them is because these are models of CFC. Well, then we have a relative notion of independence because it's relative to the model we construct, because now it's a notion of independence that changes from the classical case. But why should we, I mean, one possible reaction is, well, but we want the same notion of independence because we want the notion of independence to be absolute, because we want to know when something is really independent and when it's not. But why should we exclude them? Because in the end, these strange objects, this B, PS3, from the perspective of classical thinking, actually live in B as B, the Boolean valued models. So in the universal sets, the classical universal sets, we have classical and non-classical models of CFC. Why? But these are all models of CFC. So if we consider the collection of all models of CFC, we have classical and classical ones. So why should we exclude them? Because we're still working in V. Well, this argument is also, this argument can also be used from the classical set theories to say, well, but again, it is true that we have non-classical model of CFC, but our meta theory B is classical. So actually what we want is a match between the logic of our meta theory with the logic of the models we construct. So we want the logic of B to be the same as the logic of the B of A, which means we just want the B of B for B Boolean algebra. But the question is this argument really sound? So one of the arguments for the multiverse, as proposed by Hampkins, tries to argue that what actually looks, for example, well-founded or uncountable, actually can be seen as countable or ill-founded from a higher perspective. But then, as long as our meta theory might not be fixed, why should we base arguments on our meta theory as long as also our meta theory, being the same theory as theory in the models we construct, because CFC is a foundational theory, should be used to separate them, because also the meta theory might actually be relative to where it lives. So the question is, can we run this a similar argument to Hampkins in this case? Well, the idea is maybe yes. So what we did in this with Schrapp and Santiago was to build non-classical models within a classical environment, which is we build V of A in V. V is a classical universe. But then can we actually try to build classical models within the non-classical context? So instead of having V as our meta theory, having V of A as our meta theory, and then build a Boolean valued models in V of A. Well, if this is the case, then we can run an argument like that of Hampkins, because we can say, well, look, our meta theory is not necessarily classical. We might actually be, this V we think to be the meta theory might actually be a V of B for some Boolean algebra within a meta theory which is non-classical, which is given by some of A. So if we can build from scratches Boolean valued models within the non-classical case, then it should be argued why then our meta theory is classical, because we might actually use non-classical meta theory for all independence phenomena in the classical set theory. And even more interestingly, there is a question that might be interesting to investigate, which is the second one I listed here. Is it possible to produce a model, the A of B, meaning we start with a non-classical model, we extend it with a Boolean valid model, such that there is no Boolean algebra C which correspond to this model here? Meaning, is it possible to build Boolean valued models on top of non-classical algebra valued models that are not obtainable directly by using a construction of Boolean valued models on top of V? Because if that is the case, then this might actually justify the use of non-classical algebra valued models to get new models of classical set theory. I also had another point here, but I'll probably skip it for reason of time. So thank you very much for your attention.
Thank you, Giorgio. Thank you, Giorgio, for the nice talk. Now, questions from the audience here and also the audience online. Okay, so any questions online and people here? Let's make sure that we are still audible. Giorgio, you can hear me, right?
Yes, I can hear you.
Okay, Shorav has a question.
Giorgio.
Hi.
Hi, good morning.
Morning. Good afternoon for you guys.
Yes, so it's evening here, so almost 6, yes. Just one thing, just one comment that I was expecting that at some point probably you will tell that the inconsistency notion, like the negation with the object language and the way we defined with the not validate in this way, right? In this paper, I thought that probably at some point you will mention this thing. I think that in connection to the talk, which is a very good presentation, I liked it very much. But I think that if you just mention 1 or 2 lines on that topic, it will help to the audience to think on that. Like the inconsistency notion, you remember that we worked on that, like the it's not like it's a validating negation phi, like phi and negation phi, but it's...
Oh, yeah. Sorry.
So it's not...
Yeah, no, I think I said just a few words on that, but the notion of independence we work with is a semantic notion. Again, everything is made in semantic terms. So to have 2 models that show the independence of the formula is not to having one model showing phi and one model showing not phi, but it's about having two models, one showing phi and one not validating phi. Because in the classical case, because of the definition of the Tarski model, we have that not phi is equivalent to not validating phi. But here we have something a little bit different because the negation is not classical. So to have independence, again, in semantical terms, means to have a model which validates phi and one model which does not validate phi, which doesn't mean that it validates not phi. It's just that it semantically cannot validate phi. Okay, so this is the notion of semantic independence we work with, which needs, again, everything also in the definition of the cardinality and everything needs to be semantic, because on the syntactic side we have logic that are weak and so cannot trace differences between, for example, a formula and its negation. So in order to separate this validity and non-validity, we need to do it in semantical terms.
Thank you, Giorgio. So Professor Mihir Chakraborty has some questions, so I'm handing over the mic to him.
Thank you.
Well, thank you very much for the nice, very lucid, interesting presentation. I just want to know one thing. When you say independence of test of independence, that means you are testing independence of axioms, or which axioms you are, you will test for. As I understand, there is an object language from which you take some well-formed formula arbitrarily and test whether that, if that formula were taken in the axiom set, whether that would be independent or not. This could be one, general understanding of the supply of axioms. Others could be just ZFC or ZF, the standard things. In your case, in your all examples, you took CH, for example, or maybe some other things. So my specific question is, where from these axioms are appearing, of which independence...
Sorry, I can't hear you anymore. In this, the last 10 seconds, I couldn't hear you anymore. There is something with the microphone.
No, my question is... can you hear now? Do you hear me?
A bit better. It seems the microphone is far or...
Do you think, do you think so?
Sorry, but I can't hear you anymore.
Now, is it okay now?
It's, yes, a bit better. But yes,
No,
there's a lot of echoes.
my question is where from the axioms come, of which independence you are trying to judge or test.
Now it's better. Okay, yes, now it's better. Now the question is, which axioms can we prove to be independent? So if I understood well, so again, depending on the interpretation function, we actually get that in the PA interpretation function, all ZFC axioms are true. So this is not a question about the ZFC axioms. But any other axiom which is independent from ZFC can actually be proved to be independent in this case. And so, for example, CH, ZCH, any other possible axiom. Now, in any expression of the axiom, we need, again, to work step by step to ensure that the axiom is actually stating what is stating in the classical case. So as you've seen, there has been a lot of work to show, for example, that CH and ZCH actually say what they should. And I don't remember where Sharaf arrived in developing mathematics within these models, but I guess it's also large cardinals will be shown to be independent, exactly, but just using the height consideration. So it might be consistent for them to exist in these models, but you just can take the minimum one and it will be an independent result. So in general, it's everything that is provable to be independent in the classical case can be proven independent here.
Okay, I understand. Yeah. Okay. All right.
But just a small comment. So, if we use the normal interpretation function, there are also some other axioms with containing negation that are not provable there. So now these new axiom of CFC, some instance of replacement become independent, because the lower we go, the more independence we find. But in general, it's everything we can prove to be independent. So every axiom that can be proven independent can also be proven independent in the classical case, can also be proven independent in this non-classical case.
Okay, thank you, Giorgio. And in the interest of time, we will move to the next speaker.
Thank you.
Our next speaker is Professor Jean-Yves Béjou. Jean-Yves, are you there? Yeah, okay. Hi, we are running a bit late, hence the delay. So Professor Jean-Yves Béjou is faculty at the Department of Philosophy, Federal University of Rio de Janeiro. There are many different ways of describing Professor Jean-Yves Béjou, but if I have to pick two, he is the originator of the field of universal logic as the theory of general logical structures, and is also the person responsible for starting the World Logic Day that we celebrate every year now. Jean-Yves, over to you. Sorry, Jean-Yves, can you hear us?
Yes, sir.
Yeah.
I can hear you, but I don't understand what you're saying.
Oh.
I mean, the sound is not very good.
I was just introducing you. Once let me repeat. So Professor Jean-Yves Béjou is joining us from the Federal University of Rio de Janeiro, Brazil. He's a faculty member there. I said that there are many ways of describing Jean-Yves, but if I have to pick two, I would say that he's the originator of the field of universal logic as the theory of general logical structures, and also the person responsible for starting the World Logic Day, which is celebrated on the 14th of January every year now. Over to you, Jean-Yves.
We are not able to understand what you are saying.
Okay. Is it better now?
Yeah, it's better.
Okay, so the other microphone was translating what I was saying in a language that nobody understood. So I introduced Janives. I am not going to say what I said again, so I introduced Janives
No,
twice.
it's okay. I think you introduced the speaker, but after that, I think he has not understood what you said.
Okay, I said over to you, Janives, you can start.
But he is not understanding.
Janives, you can start, if you can hear me, Janives, you can start.
Okay, so I will start. I will start my talk. I'm not not understanding what you're saying, but I will start. Can you hear me?
Yes, sir, we can hear you.
We can hear you.
Okay, so I will start. Thank you very much for the invitation. I will share my screen now. Let me see. Can you see my screen?
Yes, we can see the screen.
Is it good?
Yes.
Okay. So we'll start my talk. Thanks again for the invitation. This title of my talk is P and not P a contradiction? Let's see. Okay. So to answer this question, I will make some connection between logic, philosophy, mathematics, and semiotics. And I think it's very important to make the connection between these 4 different fields. Before starting to answer this question, I will say a few words about Newton da Costa, because the meeting is dedicated to him. So I first met Newton da Costa in Paris in December 1990, so it's quite a long time ago. And then he invited me to work with him in Brazil. I spent 1 year. And later on, I defended a PhD with him in philosophy at the University of São Paulo after defending a PhD in Paris on mathematical logic. This photograph is during the Second World Congress on Paraconsistency, which took place in Juqué, Brazil. In 2014, I created the Newton da Costa Logic Prize for his 85th birthday, 85th birthday, sorry. And based on that, I developed the other logic prize in the world with the help of different colleagues, like in India, where now there is a Ramakrishna Matilal Logic Prize, organized by the Calcutta Logical Circle. And we start to have a World Logic Prize contest. The first edition was in Vichy, France. Second was at Unilog 22 in Crete. And the third edition will be next year for the third edition for the Unilog 25 in Peru. So everybody is welcome to join us for this meeting. This is a poster of this of the meeting that you can see on the screen. So it will be in December 25. Okay. Before that, before this meeting, I'm organizing another meeting in this year in Brazil, in Rio de Janeiro, for in memory of Newton da Costa, which will be December 24. And this meeting in Rio de Janeiro is a follow-up of a meeting organized in 2019 for at this time it was the 90 years of Newton da Costa. So you know this meeting was about creativity because Newton da Costa was a very creative logician, mathematician, philosopher. Well, he's most known for his work on Paraconsistent logic, but he has been working on many different other subjects. And for this edition of this year, it will be a more broader topic because it will be imagination, creativity, intelligence. So everybody is welcome to join us. With Newton da Costa, we wrote more than 10 papers together and a book here about paraconsistent set theory. And I also translated his most important book in French, which is called, it's a book which is about the foundation of logic. The name of this book, the title of this book in French is Logique classique and non classique. I'm saying that. And also, so the last paper we wrote together was something about religion, and the title of the paper is the following: Is God paraconsistent? Interesting question. And there is a quotation by Lars Ericsson. Lars Ericsson is a pseudonym of Newton da Costa because he liked to write some poetry, and he was using some pseudonym for that. God is the congruence of opposites. Of him, it is possible to affirm and deny everything. Now, since we are in India, there is a joke about religion, which is the following by Krishnamurti. Two friends, one of them, a bishop, die in a car crash. They go up to heaven and meet Saint Peter. Neither of them has seen too much, so he lets them in, and he said to them, "If you have any special request, tell me now, and I will see to it that it gets done." The bishop, a religious person, asks to see God. Saint Peter is startled by his request and tries to dissuade him. Seeing God is a sensitive affair. It's very shocking. Few people can stand it. If I may advise you, please don't insist on this. But the man is adamant and insists on his wish. Finally, St. Peter gives in and tells him, "Very well, if you insist, just don't blame me afterwards. Go that way and follow the signs, God. And don't forget to come back here." Off he goes to see God, while his friend waits with St. Peter for his return. It takes 10 to 15 minutes before he returns. He's a mere shadow of himself, as pale as a ghost, and staggering about in deep shock. His friend is concerned to see him in this state and says, "By Jove, what happened to you? What was he like?" But the man can only moan, "She is black." So it's a joke. By the way, Newton da Costa liked very much to make some jokes, but now let's come back to serious things, if I may say. So it's common nowadays, even among deviant logicians, as sometimes they are called, to say that P and P is a contradiction. Is that right? That's the question I will try to answer today. Okay. There is a famous quote by the French philosopher and mathematician Blaise Pascal. Yeah, I will read it original in French. Je ne dispute jamais du nom pourvu qu'on m'avertisse du sens qu'on lui donne. I never quarrel about a name provided I am appraised of the sense in which it is understood. Okay, so in some sense, we can call what we want. We can call what we want contradiction. But, I mean, at least we need to give a specific meaning to these words. That's the point, I mean. And most of the time, there is no specific meaning giving. So there is a kind of ambiguity all the time. So that's what we need to have in mind when we are trying to answer this question. Sure. So, all right. So, many people say P and P is a contradiction. But what does it mean? So we have to understand what is the meaning of this symbol, small symbol, which is nowadays used most of the time to speak about negation, and the word contradiction. And also, of course, the P, what is P? So we have to go in details about all this kind of things. Most of the time, people don't go in the detail about that. They think they understand. But it's okay if you ask some question to check if they have understood the precise meaning of all these components, you will see that most of the time they don't really know how to answer. So for modern logician, P and not P is a contradiction. It seems obvious. But if we know a bit about the story of logic in ancient Greece and ancient India, this is completely meaningless. So this is an important point. Why it is meaningless? Because not going back so much in the past, we can see nowadays that we can formulate, that we can interpret this proposition, this sentence, P and not P is a contradiction, in many different ways. We can put some quote while putting P. Someone may say, well, we are not talking about proposition, we are talking about sentence. So you will put S. Someone may want to put X because to let some indetermination about what we are talking. Instead of hand, we can put the kind of symbol for collective, and so on. We can also put a pair like that, avoiding to use the conjunction. And all these variations are important at some point. But I will not, in this talk, I will not make an analysis of all these details. But I just want to point that there are all kind of ambiguity about how to interpret this in formal logic nowadays. So when we have this declaration, P and not P is a contradiction, we see that this notion of contradiction depends on the notion of negation, or involves negation. Yes. But Wittgenstein formulated contradiction not using negation. And it's very funny because Wittgenstein is very famous at the beginning of the story of modern logic. He presents a definition of what is a contradiction in the Tractacus. I will make some comments about that. In this famous booklet, Wittgenstein defines at the same time what is a tautology, which is now a very famous notion, which was not existing before him. It's good to remember that. At the same time, in the same paragraph, he defines what is a contradiction. Let's see. This is 4.46. Among the possible groups of truth conditions, there are two extreme cases. In the one case, the proposition is true for all the truth possibilities. What Wittgenstein is calling truth possibilities is what we are calling valuation nowadays. In the one case, the proposition is true for all truth possibilities of the elementary proposition. We say that the truth conditions are tautological. In the second case, the proposition is false for all the truth possibilities. The truth conditions are self-contradictory. In the first case, we call the proposition a tautology. In the second case, a contradiction. So you can see in these definitions, there is no negation involved. No negation at all. Yeah. Is it a good, shall we follow Wittgenstein? Is this definition good definition? There is a confusion because nowadays people are making the confusion about the notion of contradiction between this definition of Wittgenstein and the first I was presenting today, P and not P, because they are equivalent in classical logic. So if you take the truth table of negation, classical negation, P and not P is a contradiction because of the definition of contradiction by Wittgenstein and because of the definition of negation with this truth table. You see, there are two things involved: the definition of contradiction not depending of negation and the definition of negation using a truth table. Now, if we are going out of classical negation, these two things will disconnect. So, first of all, the Tractacus is not the Bible of logic, which it was a very important book at some point. And now, some sense, Wittgenstein is out of fashion. I was invited, by the way, to take part to this famous international Wittgenstein symposium. And in this talk I presented, it was like some 5 years ago. My objective in this talk was to make a comparison between the way that we understand propositional logic today and the way that it's presented in the Tractacus, especially the question of the semantics, because the semantics of the propositional logic, classical proposition, was presented by Wittgenstein with this notion of truth possibilities and truth tables and so on, combinability. But, well, we can define in a different way negation and contradiction. I will explain. So I think it's better to call a proposition which is always false an ontology. And some people, in some books, you can find this terminology. It's better because it's more neutral and it's make a connection with tautology. We have a nice pair, tautology, ontology, logical truth, logical facility. And we see that if we use this word ontology, P and not P is a particular case of ontology, according to classical negation, you know. So, for example, in the same way that P or not P is a particular case of tautology. We don't have we don't have a good reason to identify a tautology with excluded middle. So to call an ontology contradiction is the same as to call a tautology excluded middle. So you are using a particular case. So I think that's why the use of this terminology originated by Wittgenstein contradiction is not good, especially if we go out of classical logic. But even if we are inside classical logic, even within classical logic, I don't think it's a good choice. Okay. Then how to define contradiction? Well, if we don't follow the definition of Wittgenstein, which is I will call ontology, what can we do? I will speak a bit here about the square of opposition. The square of opposition is a famous diagram. It's related with a theory which is very old, back to Aristotle. And according to these theories, there are three notions of opposition: contradictories, contraries, and subcontraries. So we say that two propositions are contradictories, they cannot both be true and cannot both be false. And they are contraries if they can both be false but cannot both be true. Yes. And they are subcontraries, they can both be true but cannot both be false. This can be understood as a relation between two propositions, but also we can have an interpretation which is related with some sets, as you can see here. So the notion of contradiction is a classical complementary of set theory. The contrary is something like that. Disjoint, there is disjoint, but there is space out. And the subcontrary is there is no space out, but there is an intersection. So I have been working also on the square of opposition since a couple of years. We have organized different meetings in different places. The next one, so these are the previous edition. The next one will be soon, in about 2 weeks. No, for 3 weeks, if I may say, in Costa Rica. Everybody is welcome to join us. So, if we follow, so as you see, in this theory of the square for position, there is a notion of contradiction. And in this case, contradiction is a relation between two propositions, not involving negation. Not involving negation. Because when we say two propositions can both be true, can both be false, cannot both be true, cannot both be false. Any proposition, yeah. And according to this definition, we will not say that P and Q is a contradiction when P and Q can both be false. I will give you an example. When we ask someone to give a concrete example of contradiction, you can do that, you know. It's a kind of funny game. You ask someone, what is a contradiction for you? Give me an example, you know. And many people will give as an example a round square. Round square. This example has been presented during the history of philosophy. Round square is a typical, for many philosophers, it was a typical example of contradiction. But round squares, I wrote a paper about that, which is I been published in the book we have edited after the Congress, the 5th World Congress of Paraconsistency that we organized in Calcutta in 2014, 10 years ago already. Yeah. And well, why round square are not contradiction? Because something can be neither a square, neither a circle. It's typically an example of contraries, not contradictories. If you know, if you think about that, it's obvious that this is not a contradiction. It's a contrariety. Yeah. And this distinction between contradiction and contrariety was already made by Aristotle. It's funny that until now people are not making this distinction. Well, now let's go to another case. So, in the same way that we will not call P and Q a contradiction if they can both be false, also we will not say that they are contradiction if they can both be true. Because in this case, they are not contradictories, they are sub-contraries. You see? Okay, so that's the important terminology of the square proposition. Now, that's the point. But what I would like to say now in this part of the talk is that nevertheless, we can still call this a negation. We can still use the word negation when P and not P are not contradictory, like in paraconsistent negation, like in intrinsic, like for intrinsic negation, like for minimal negation. These are two different things, you know. They are two different things. So, what is a negation? We have to inquire now about negation. Before going to this slide, I would like to say that during many centuries before the development of modern logic, well, people they were saying we have two or three basic principles in logic: the principle of non-contradiction, the principle of excluded middle, the principle of identity. Well, but these principles were not formulated clearly. And the important point of modern logic is that there was a decomposition of the properties of negation. I will show you here. So here we have the different axioms, rule, principle for negation. The decomposition of this is a kind of decomposition of the principle for negation. And what we can what we can show that what we know nowadays is that this one here, from this one we can have all the other properties of negation, in particular this one, this one, this one. if we take on, and this one also. Now, if we, all these principles, there is no overconnectives at negation. Now, if we go to this part here, this interaction between negation and overconnectives, these are famous De Morgan laws. So nowadays we can decompose negation. So the question we can ask is, well, what's shall we call a negation only if we have all these properties together, or if we can still call a negation when we have only part of these properties? Well, there is nowadays a consensus to say, well, if we have only one part, like for example in implicit logic, we can still speak about negation because we have already some strength, some good strength of negation. So implicit logic was the first logic promoting a negation which is not classical logic, and everybody in some sense at some point agrees to still call this a negation. The same with De Morgan negation, and also in paraconsistent logic nowadays. Right. So people are using this symbol, yeah. The same symbol. Sometimes they change the symbol, yeah, but shall we change the symbol? For example, shall we use a different symbol if we are talking about implicit logic or not? The same. That's a very important question about symbolization in mathematics and in mathematical logic. So there are different interpretations of this symbol. So this symbol may denote different things and may have different meaning. They have different meanings. Well, that's at some point, at the beginning of modern logic, Frege and Wittgenstein, they wanted to make a perfect unambiguous language. But nowadays, nobody wants to do that, because we know that what we call ambiguous language in French, they are very useful, and this is what mathematical symbolism shows. Every day, mathematicians are using the same symbol to denote different things, and this is very useful, but we have to be aware of this variation of meanings. There is a very interesting book which was written by a friend of mine who died a few years ago, which is called The Symbolic Revolution, where he explained how modern mathematics developed using symbolism. Sarfati was a great specialist of George Boole. I myself wrote a book, a paper about George Boole. So George Boole, in this famous book, The Law of Thought, he proved that the principle of contradiction is the consequence of x to the square is equal to x. His proof, in this paper I wrote, I explain the detail of this proof. Why, according to Boole, this is true, and why, for this reason, Boole had this idea, which nowadays seems very strange, that x to the square is equal to x is a fundamental law of thought. No, more fundamental than the principle of non-contradiction, because he proved that we can deduce the principle of contradiction from that. But how did he prove that? By using symbolism in a certain way, in a way which is quite similar to the way it is used in symbolic algebra. And by the way, Boole was raised in the school of symbolic algebra, which was a very important school in the history of mathematics, which was developed in the beginning of the 19th century in England. So he decided to use symbolism also in logic. Symbolism, in this sense, means there is a variation of meanings. Yeah. I also wrote a paper about the number one, which was published by in the special issue of the Journal of Indian Council and Philosophical Research, edited by Amir Chakraborty and Michel Friend. And in this paper, it's related with this question of symbolism, because I explain what is that the number one, the same symbol, the same sign, the same name, is at least 5 different meanings. Yeah. So in mathematics, it's quite common to make the variation of the meaning, but up to some point. let's have a look at this symbol. This symbol is used for order relation, yeah. And in general, this symbol has obeying at least the two following axioms. The first one, which is called antisymmetry, and the second one, which is called transitivity. But there is a variation of meanings, especially we think about model theory. Model theory is an important part of modern logic, which was developed mainly by Alfred Tarski, making a connection between the language and the interpretation, the semantics, as we say sometimes. So there are thousands of different models of this order relation, which are different from each other, incompatible from each other. For example, if you consider a total order, a partial order, that is compatible, But at the same time, they have something in common, which is these two axioms. And let's see, discrete, lattice, or something like that. So I think this is a nice example. It's a very simple example that everybody can understand. That the meaning of this symbol is changing. But at the same time, there is something in common between all this model of order theory. There is something in common, but some theories of orders are incompatible with each other. Okay, now can we do this all the time? Well, as you can see, here it makes sense because we have some basic axioms that every order theory of order obeys. Now if we go to the zero, let's see zero. So zero, the properties of zero in mathematics, people use the same name, the same symbol for zero as a natural numbers and zero as a rational numbers, But it has not the same property because as a rational number, it is not the first number. As a natural number, it is the first. Okay, but zero as a rational number and zero as a natural number, they have the same two. They have at least two in common two properties, which are the following: zero plus something is something, and zero times something is zero. So the question now: would it make sense to talk of a zero being none of these two axioms and still using the same sign? It will be the same as as talking about relation. It will be the same as It will be the same as still speaking about an order relation without these two axioms, because there are the two basic axioms for a relation of order. So we can make a variation up to some point. Now, what about negation in logic? Now, what about negation in logic? Does it mean saying to take off a negation, not obeying one of the two following axioms, or even none? P or not P? And from P and not P, I can deduce, sorry, there is a typo here, I can deduce not P or any properties. Well, can we still about negation in this case? Well, what we have here is it's a situation when we can, maybe if we have enough properties, we can still about negation, but we cannot speak about negation if we don't have all the fundamental properties. So what I want to say is there are some good reasons to still call negation a unary collective, such, for example, that P and not P can be true together, or such from P and not P we cannot deduce anything. There are some good reasons. What are these good reasons? Is that this negation still has half of the properties of classical negation. So half is good. And we can say many properties of negation are compatible with that. So it is not the same as still calling zero a neighbor such that 0 times something is not 0. In mathematics, a lot of people, these people are not taken seriously, Sometimes, it's like crank people. Every day, you can see a paper on the internet saying, well, I have zero, such that zero something times something is not zero. You know, but can we still seriously call this a zero? We have to understand exactly what it means. Okay. So even this will be the conclusion of my talk. Even if we can still call a negation unary operator not obeying the excluded middle, not obeying the principle of explosion, even if we can still call this a negation, is not good to call P and not P is a contradiction. These are two different things. Because this is a source of confusion, as I was explaining in the previous parts of my talk. It's better to avoid that unless one is a classical logician. Because in paraconsistent logic, P and not P is not a contradiction. Yes. And in intuitionist logic, also P and not P is also not a contradiction. Even if we can still call this a negation. So this is the end of my talk. Thanks.
Thank you, Janives,
Yeah.
for the nice talk. Can you hear me now? Can you hear us?
I don't hear anything. So maybe if there is a question, maybe it's better to write it or something. No, I cannot hear anything. Thank you.
Okay, so we are trying from a different device to send voice messages. So I guess you can hear us now, Janives? Okay, so now it's audible?
Yeah, now I understand. Now I can listen. Yeah.
Any questions from the audience here? Okay, Janif, it seems that there are no questions.
Okay.
So
Thank you. Okay, thank you very much. Bye-bye.
bye.